or FSTP, was also established around this time and still remains as one of the university's primary extension programs. In the field of instruction, the book titled Integrating Sustainable Agriculture in the BSA Curriculum, the UPLB College of Agriculture Experience, was published in 1999. At present, the College of Agriculture and Food Science, or CAFS, continues to be the premier institution of higher learning in agriculture and food science, and remains committed to nation building through its instruction, research, and extension programs. In order to produce the best graduates, all of our courses are outcomes-based education, and continuous improvement of the curriculum is being practiced to meet the challenges of the 21st century. As testament of excellence, CAFS is constantly recognized by different organizations. In research, we continue to implement relevant studies with focus on the 12 priority commodities to address food security. Moreover, technologies are constantly developed to aid in responsible food production. Supplementing these are extension activities to disseminate the knowledge generated to improve food productivity and livelihood of the people. We believe that present technologies will future-proof our food systems. Some of our notable developments are iDetect, Coraginam, Plant Health and Pest Clinic, Pest Management Tools and Techniques, Smarter Pest Identification Technology or SPITech, Snap Hydroponics, Drone Technology, Rapid Immunofilter Assay for Virus Indexing, Nanofertilizers Fertigrow, Hormogrow, Nanobiosensors, and Biochar. We at the College of Agriculture and Food Science will continue to promote and nurture a culture with innovative yet conscientious minds and cutting-edge skills to lead and serve the country and the region. We are one college with one goal towards sustainable food systems.
When I will grow up, I know.
food security policies, confusing field practices. While Philippine agriculture has been a major arm of the government in achieving its long-term goal of food sufficiency, its objectives can only be attained fully in partnership with a strong pest management institution. The answer: the National Crop Protection Center. The National Crop Protection Center. The remnants of Rodent Research Center in 1968 paved the way for the establishment of the National Crop Protection Center on May 19, 1976, by virtue of Presidential Decree 936. Its founder, Dr. Fernando F. Sanchez Sr., exerted all efforts in expanding the rodent studies into more comprehensive pest management programs by forming teams of experts in rice, corn, vegetables, pest surveillance and forecasting, plant quarantine, pesticide chemistry and toxicology, and training and extension. Thus, the center's existence has been strengthened to provide solutions to the country's pest problems by developing, adopting and extending appropriate pest management technologies to farmers and formulating appropriate recommendations for use by government policymakers. An advisory board spearheaded by the Department of Agriculture served as guide in pursuing the goals of the center. After 12 years of clustering, the UP Board of Regents approved the restructuring of the College of Agriculture, renamed it as College of Agriculture and Food Science, and dissolved all clustered units and institutes to form independent units, again including NCPC. Today, the center rises up as a center of excellence in pest management, with its new leadership and experts that would continue the works and realize the vision of world-class excellence in crop protection and pest management. The center stands alongside premier UPLB institutions at the Agricultural Science Park of the University of the Philippines, Los Baños. NCPC is headed by a director, deputy director, and division heads, supported by a number of research and extension staff, and backed up by administrative personnel, unified by the standing goal to support agriculture programs to ensure food security, environmental sustainability, and the upliftment of the general public's quality of life. The staff work together harmoniously with each other and devotedly pursuing productivity. Researchers occupy laboratories with cutting-edge equipment to support pest management researches in the fields of plant biosecurity, pest management, pesticide management, and public service. Extension services are also active components of public service. Technical services are focused on plant health clinic, the quick response team wherein NCPC addresses serious pest problems through quick response to pest outbreaks. The center also caters to pesticide residue analysis and pest database management. NCPC leads in national research and development programs with solid international and local partnerships, regional crop protection centers, Department of Agriculture, regional field offices, Bureau of Plant Industry. The center's advisory board members that continue to provide guidance in the performance of its RDE functions are respected and well-accomplished institutions. NCPC strengthened and dynamic researches, human resources, and multi-institutional collaboration continue to meet the needs of various stakeholders, including the academe, LGUs, farmers, policymakers, and other government institutions. Welcome to the National Crop Protection Center.
Magandang umaga po sa ating lahat. Magandang araw po sa ating mga attendees dito sa Zoom space at sa ating mga taga-subaybay dyan sa FB Live at saka sa YouTube Live. Welcome po sa NCPC Webinar Series 2021. Ang webinar po na ito ay bahagi ng ating regular activities dito sa National Crop Protection Center, College of Agriculture and Food Science, UPLB, na magbahagi ng mga kaalaman ukol sa pamamahala ng iba't ibang peste at sakit ng mga halaman. Mary Joy Mendoza po, ang inyong lingkod, isang university researcher dito sa NCPC. Ako po ang inyong magiging MC para sa webinar ngayong umagang ito. Okay po. So, ang topic po natin sa ating last webinar ay patungkol sa management ng onion armyworm, kung saan naibahagi po ng ating mga speakers ang pagkilala, pagsubaybay at pamamahala ng harabas ng sibuyas. So, nagkaroon po tayo ng topic sa biological studies at monitoring and advisory system ng harabas or harmonia. Ngayon din na ibahagi po ang botanical and microbial control of onion armyworm, cultural management at insecticide resistance management, pati na rin po ang post-harvest aspects nito. So, ngayon pong ngayong araw po ay siksik na naman po sa kaalaman ang ibabahagi ng ating mga speakers about po sa isang mapaminsalang peste na kung tawagin po natin ay fall armyworm o harabas ng mais. Ito pong insektong ito ay isang malaking pangamba sa mga nagtatanim ng mais, hindi lamang po dito sa Pilipinas kundi maging sa ibang bansa. Kaya naman po tiyak na marami po tayong mapupulot na impormasyon ngayong umaga sa ating mga eksperto, sa ating mga resource speakers. Kaya naman po kung handa na po kayo, maaari nyo po bang i-click ang ating thumbs up reaction button para po sa mga participants dito sa Zoom space. Makikiclick naman po ng ating thumbs up react button. Sige po. Okay, handa na po ba tayong lahat? Okay. So, paalala po lamang sa webinar na ito ay maaari nyo pong mapanood sa 3 platforms. Dito po sa Zoom. Live din po tayo sa NCPC YouTube at sa ating NCPC Facebook page. And for our attendees sa Zoom space, maaari po kaming makiusap po na makimute po ng ating microphones. You can use our chat box para sa inyong mga katanungan or magbigay po ng comments and we shall read it or ask it for you. So pwede din po kayong mag-message sa ating Facebook at YouTube comment section. In case na nais nyo pong magtanong live, please use our raise hand button at doon sa ating pong Q&A forum portion. Upang makatanggap naman po ng e-certificate, mangyari lamang po na maki-fill out ang ating evaluation form na ipa-flash towards the end ng webinar na ito. Sa mga hindi po nakatanggap ng e-certificate sa mga nakaraang webinar, ngunit kayo naman po ay nag-fill out ng evaluation form, maaari nyo pong i-check ang inyong mga spam folder sa inyong email account. Okay po. So, nais po natin i-acknowledge ang ating mga taga-subaybay. Meron po tayong 102 participants na dito sa Zoom space. Okay, so gusto po nating malaman kung taga saan po kayo. Sige po. Maaari po bang heart react kung kayo po ay taga Luzon? Sige po. Ayan. Okay? Ayan, taga Luzon. Okay, salamat po. Maraming salamat sa ating lahat. Ngayon naman po ay clap react kung kayo ay taga Visayas. Ayan, nakikita na ba tayo? Taga Visayas. Ayan, meron din. Ano? So, kung taga Mindanao naman po, maki-thumbs up react. Thumbs up. Ayan, meron din po tayong from Mindanao. Okay, magandang araw po sa ating lahat. So to formally start our webinar, we would like to call on the NCPC Director, Sir Melvin Iguenga, for the opening remarks. Sir Melvin.
Maligayang pagbati sa inyong lahat at welcome sa webinar na ito. Nawa ay nasa mabuti kayong kalagayan at ligtas sa pandemyang umiiral sa kasalukuyan. Kagaya ng maraming institusyon ngayon, ang NCPC ay tumutugon sa hamon ng pagbabago at gumagawa ng mga kaparaanan para manatiling matatag at nagagampanan ang pagsilbi sa ating mga magsasaka sa kanilang mga problema sa peste at sakit ng halaman. Maraming salamat sa Department of Agriculture, sa Department of Science and Technology, sa UP, at iba pang mga funding agencies na patuloy kaming sinusuportahan sa pagtuklas ng mga bagong kaalaman sa pagsugpo ng mga peste at sakit ng ating mga pangunahing tanim. Sa umagang ito, aming ibabahagi ang mga bagong kaalaman at pamamaraan upang masolusyonan ang kasalukuyang pangunahing problema sa mais, ang Fall Armyworm o PAW. Ito ay ibabahagi sa inyo ng aming mga siyentipiko at eksperto sa umagang ito. Sila ang gumugol ng mahabang panahon ng pananaliksik para matulungan ang mga magmamais. Pag-uusapan natin ngayon umaga ang mga sumusunod na topics: biology of PAW, modeling and remote sensing of the fall armyworm infestation in corn, entomopathogenic nematodes as biological control agents against PAW, potential of entomopathogenic fungi against PAW, natural enemies of PAW, insecticide resistance management, at Grow Asia's Asian PAW Action Plan. Nawa sa mga topic na ito ay marami kayong matutunan at inyong magamit sa inyong pagsasaka o kaya inyong maibahagi sa iba pang nangangailangan ng mga ganitong impormasyon. Sa ganitong paraan, tayo ay uunlad at makakatulong sa pag-asensyo ng agrikultura ng Pilipinas. Muli, maraming salamat sa inyo. Magandang umaga. Mabuhay tayong lahat.
Ayan, maraming salamat po, Sir Melvin. So before po natin i-welcome ang ating first speaker, may I request everyone to open your video and wear your best smile para sa ating virtual photo op. We also invite our speakers. Kung nandito po kayo sa Zoom space, makiki-open na lang po ng inyong video. Miss Charlotte?
Yes po. Okay, so let's just wait for the others na makapagbukas ng kanilang video. And so we have 123 participants. Kaya ipakita nyo naman po ang inyong nagagandahan at naggagwapuhang mga mukha. Okay po, so let's start. Okay. 1, 2, 3, smile. Okay, next frame po. 1, 2, 3, smile. Okay, next po. 1, 2, 3, smile. Okay, last two. 1, 2, 3, smile. Okay, and lastly. Okay, 1, 2, 3, smile. Okay na po. Thank you very much.
Thank you, Miss Charlotte. Okay, so I think everything is in order. I think we are now ready to listen sa ating mga speakers. Pito po silang resource speakers natin ngayong umaga. Kaya, ayun, hindi na po natin patatagalin pa. So, for our first speaker, si scientist Marcela Navasero to discuss ang biology ng fall armyworm. Siya po ay isang university researcher dito po sa NCPC at eksperto pagdating sa pag-aaral ng harabas. Ma'am Sally?
Magandang umaga po sa ating lahat. Sa umagang ito ay tatalakayin natin ang tungkol sa fall armyworm, its biology and key characteristics. Ang fall armyworm po ay nabibilang sa domain na Eukaryota, Kingdom Metazoa, Phylum Arthropoda, Subphylum Uniramia, Class Insecta, Order Lepidoptera, Family Noctuidae, Genus Spodoptera, at Species Spodoptera frugiperda G.E. Smith. Ito ay unang na-describe ni Ginoong J.E. Smith in 1797. Ang FAO ay nag-originate po sa Americas at ito ay unang napa-report sa Africa noong 2016, 2018 naman sa Indian subcontinent at noong nakaraang taon ito ay kumalat na sa Africa at Asia, kabilang na dito ang Pilipinas. Makikilala ang FAO sa pamamagitan ng mga distinguishing characteristics sa uod at sa katawan at ulo ng uod. Makikilala ang larva sa pamamagitan ng mapusyaw na linya sa kanyang likod at may itim o dark clutter line sa kanyang tagiliran. At makikita rin na kapansin-pansin ang apat na dots o pinakila na arrange into square sa hulihang bahagi ng kanyang tiyan. At ang ulo naman nito, kapansin-pansin ang inverted Y shape. Sa ibang bahagi naman ng katawan ay kapansin-pansin din ang apat na pinakula or dots arranged in trapezoid sa una hanggang ika-pitong abdominal segment at ang apat na pinakula naman ay arranged in straight line sa thoracic segment 2 and 3. Makikilala rin ang FAO sa pamamagitan ng kanyang adults, lalong-lalo na sa lalaki, na ang unang pares ng pakpak o forewings ay may distinct markings na makikita na orbicular spot na kulay brown, oval, and oblique. At meron ding row of small black markings near apical margin of the wings. At ang apex ng forewings ay kulay white. Ang hindwings naman nito ay dirty white with dark brown borders at the outer margins. Ang babaeng FAO ay walang gaanong pagkikindanlan sa pamamagitan ng pakpak. Lamang ang forewings nito ay grayish brown o mas matingkad kesa sa lalaki. Ang hindwings nito ay dirty white with dark brown borders at the outer margins. Kilalanin naman natin ang iba't ibang stages ng uod ng FAO. Ipinapakita ang mga itlog ng FAO na inilagak sa laboratorio. Ang itlog ay in mass at ang isang egg mass ay inilalagak ng 11 kada isang inahin. At ang isang egg mass ay maaaring 110 na itlog kada egg mass. Ang isang inahin ay nakapaglalagak on the average ng 1,033 eggs na kung mapisa ay umaabot ng in total 76.37%. Ang isang itlog ay may sukat na 0.38 millimeters ang diameter at 0.26 mm ang height. Ito ay may kulay dilaw, pagbagong lagak, turning brown then black before hatching. Ang incubation period ay 2 hanggang 3 araw. Ang first instar larva naman ay napakaliit at may sukat lamang na 1.77 mm at may lapad na 0.23 mm. Ang kanyang ulo ay may sukat na 0.22 mm at ito ay tumatagal lamang ng 2 hanggang 3 araw. At sa kapansin-pansin na rin ang 4 na dots o pinacula sa hulihang bahagi ng kanyang likod. Ang second instar larva naman ay may sukat na 2.79 mm at may lapad na 0.38 mm. Ang head capsule ay may sukat na 0.35 mm. Ito ay tumatagal din ng 2 hanggang 3 araw at kapansin-pansin na ang papalaking 4 dots sa hulihang bahagi ng kanyang katawan. Ang third instar ay higit na mas malaki kesa second instar. Ito ay may sukat na 7.41 mm at lapad na 0.89 mm. Ang head capsule ay 0.61 mm at ito ay tumatagal ng 2 hanggang 3 araw. At kapansin-pansin ang 4 dots forming a square sa hulihang bahagi ng katawan. Ayan ang relative sizes ng first, second, and third instar larvae ng fowl. Ang fourth instar larvae ay higit na malaki kaysa third instar. Ito ay may sukat na 14.57 mm at lapad na 1.86 mm. Ang head capsule ay 0.95 mm. Ito ay tumatagal ng 1 to 2 days. At ang 4 na pinacula ay matingkad sa hulihang bahagi ng katawan. Ang fifth instar larvae ay mas malaki din kesa sa higit na malaki kesa fourth instar larvae at ang na may sukat na 21.25 mm at lapad na 2.99 mm at ang head capsule ay 1.46 mm. Ito ay may tumatagal ng 1 hanggang 2 araw at mas kapansin-pansin na ang 4 dots sa hulihang bahagi ng katawan. Ang sixth instar at pinakahuling yugto ng larval stage ng fowl, ang pinakamalaki sa lahat. Ito ay may habang 30.79 mm, lapad na 3.82 mm at head capsule na 2.03 mm. Ito rin ang pinakamahabang yugto ng uod ng fowl na tumatagal ng 3 to 4 days at kapansin-pansin ang 4 na dots forming a square sa hulihang bahagi ng katawan. Ito ang relative sizes ng older larval instars ng fowl na binubuo ng 4th, 5th, and 6th instar. Ito ang pre-pupa ng fowl o ang huling araw na 1 hanggang 2 araw ng larval stage ng fowl na hindi na siya kumakain at lumiliit at siya ay may haba lamang na 19 mm at lapad na 4 mm. Ang head capsule ay 2.03 mm at ang 4 square dots ay kapansin-pansin sa hulihang bahagi ng katawan. Ang pupa ng fowl ay typical na obtect pupa na sa simula ay greenish white na nagiging brown at nangingitim prior to adult emergence. So nagpo-pupate ito sa dahon o tissue paper o lupa sa laboratorio at sa field ito ay makikita sa soil. Ang pupa ay may habang 14.1 millimeters, lapad na 4.21 millimeters na tumatagal ng 9 na araw. Ang pagkikilanlan sa male at female na pupa ay yung dalawang slits ay magkahiwalay sa babae at ito naman ay magkalapit sa lalaki. Ito ay makikita lamang sa microscope. Ang ating adult male ay may tumatagalang buhay in 9.3 days. Ang wing expanse o lapad ng pakpak ay 32.66 millimeters. Ang body length ay 13.33 millimeters. Ang babaeng moth ay may pre-oviposition period na 3.5 days, oviposition period na 3.69 days, at post-oviposition period na 2.81 days. Ang buhay nito ay tumatagal ng 9.85 days. Ang wing expanse niya ay 32.81 millimeters at ang body length ay 12.2 millimeters. So, ito ang kabuuang life cycle ng fowl. A and B, magkaiba ang itlog nito kapag inilagak sa wax paper sa lab, sa A, at sa dahon. Ang inilagak sa wax paper ay walang balot na cottony substance, habang ang inilagak sa dahon ay nababalutan ng makapal na cottony substance. Ipinapakita din dito ang egg mass na nagsisimula ng mamisa. Ang ikalawang linya ay ipinapakita ang una hanggang ikatlong yugto ng larval stages. Makikita rin dito ang pinagkainan ng maliliit na uod ng fowl. Sa ikatlong linya, ang pinapakita ang 4th, 5th, and 6th larval stages ng fowl. At makikita na pagdating ng ika-6 na yugto, pinakamalaki na at kapansin-pansin na lalo ang 4 square dots o pinacula sa likuran ng uod. Sa ika-4 na linya ay ipinapakita ang prepupa, umuka sa tissue paper, sa dahon at tissue paper na sa laboratorio. Ang huling linya, ipinapakita ang adult male sa kaliwa at ang adult female sa kanan. Ipinapakita natin dito ang kabuuang inog ng buhay ng fowl, ang iba-ibang duration ng itlog, larva, at pupa. Ang lalaking larva ay tumatagal ay may habang 14.73 days, habang ang babae ay may habang 14.4 days. Ang pupa ay may habang 9 days at ang babaeng pupa ay 8.5 days. Kabuuan, mula itlog hanggang adult, Ang lalaki ay may habang 25.73 days, habang ang babae ay 24.90 days. Pinapakita natin kung paano ang oviposition o pangingitlog niya sa laboratorio, sa wax paper at sa dahon ng mais. At ang haba ng isang egg mass ay umaabot ng 30.5. Ang mga sumusunod, ang iba pang noctuid pest na namiminsala sa mais. Ang una ay ang uod ng Spodoptera exenta. Ang sumunod ay uod ng Spodoptera exigua, ang cutworm o Spodoptera ritura, ang Spodoptera mauritia, mitim na separata, Helicoverpa ermigera na may brown at green forms, at ang panghuli ay ang corn semilooper, Chrysodeixis eriosoma. Ang ibang Lepidopterus pest na ito ay makikilala mula sa FAO sa pamamagitan ng presence or absence ng inverted Y. Ang unang picture ay ulo ng FAO na ang inverted Y niya ay nakabilog. Ang inverted Y ng Spodoptera exenta ay mas makipot. Ang sa Spodoptera exigua or onion armyworm ay lighter. Ang sa Spodoptera litura naman ay manipis ang linya. Ang sa Spodoptera mauritia ay mapusyaw ang kulay. Samantalang ang sa mitim na separata ay black. Ang sa Helicoverpa armigera ay hindi kapansin-pansin. Samantalang ang semilooper ay ang inverted Y niya ay hindi kulay puti. Ito naman ang feeding damage ng early instar larvae ng FAO sa laboratorio at sa bukid. Kapansin-pansin ang mapuputing pinagkainan ng maliliit na uod sa dahon. Ipinapakita naman dito ang feeding damage ng late larval instars, so 4 to 6 instar larvae ng FAO sa vegetative na corn. Kapansin-pansin ang malalaking butas na pinagkainan ng uod at ang mga ipot ng uod na nakadikit sa dahon na kulay brown. Sa kanan ay makikita ang pinsala ng fall armyworm larvae sa tassel at sa corn cobs. Naitala rin ang damage ng FAO sa ibang crops kagaya ng sugarcane, na ang pinsala niya ay katulad din ng sa corn, kinakain ang dahon at nagiiwan ng brown na excreta o ipot. Kamakailan, ang FAO ay nakita ring naminsala sa rice. Ito ay sa kagandahang loob na ni Ginang Mindaflor Gelsote Masin Aquino ng Regional Crop Protection Center 2 na naitala nila ang FAO at FAO damage sa Pateng, Gonzaga, Cagayan noong May 17, 2021. Ito ay umabot sa Quirino noong May 28, 2021. Ipinapakita ang FAO na nasa ika-6 na yugto o 6th larval stage na umatake sa palay. Mga reported plant host ng FAO na nandito rin sa Pilipinas, kagaya ng okra, sibuyas, bawang, uray lalaki, mani, asparagus, cauliflower, cabbage, papaya, watermelon, Arabica coffee, melon, cucumber, Bermuda grass, paragis, strawberry, soybean, sunflower, sweet potato, mango, saging tobacco, patani, bitsuelas, bayabas, labanos, castor, rose, kamatis, talong, patatas, paayap, grapes, mais at luya. Ang fall armyworm ay cannibalistic sa ibang larvae kagaya ng true armyworm. Kinakain ng fowl larvae na patay na larva ng true armyworm. Kapansin-pansin na kayang patayin ng fowl ang higit na malaking uod ng true armyworm kesa sa kanya. Ang fall armyworm ay cannibalistic din sa Asian corn borer. Ipinapakita dito na kaya niyang patayin at kainin ang higit na malaking uod ng corn borer. Ang fowl larvae ay cannibalistic din sa kanyang kapwa fowl larvae. Ipinapakita dito na ang mas malaking uod ng fowl ay nagkakanibalize ng mas higit na maliit na uod ng kapwa niya, fowl. Ang fowl ay inaalagaan namin sa laboratory gamit ang dahon ng mais. Pag single culture o isahang pagpapalaki, gumagamit kami ng Petri plates na plastic. At sa group rearing naman, gumagamit kami ng plastic vats. Pwede ring i-rear ang fowl sa potted seedlings ng corn, kagaya ng pinapakita dito. Nire-rear din namin ang fowl larvae sa diet. Inilalagay sa plastic cup ang diet at dito inilalagay isa-isa ang fowl larvae hanggang sa mag-pupate. Pwede rin i-rear ang fowl larvae sa bush sitaw, sa burnt onion, at cyperus area, isang uri ng sedge. Lamang mas mabilis paramihin sa dahon ng mais, kaya sa kasalukuyan, sa dahon ng mais na lamang namin pinapalaki ang fowl. Sa pagpapaitlog ng fowl, gumagamit kami ng maliliit na plastic cylinders kung single pair o isang pares adults ang aming pinapaitlog, at sa mass pairing naman, gumagamit kami ng mas malalaking plastic na oviposition cages. So, nais naming pasalamatan ang DA BAR at DOSTP card para sa financial support ng dalawang project, at ito ang aming mga project staff na tumutulong sa paggawa ng experiments sa laboratory. Maraming salamat po.
Maraming salamat po, Ma'am Selly. Marami po tayong natutunan na hindi lang pala mais ang inaatake ng fall armyworm. Napakarami pong hosts na pwede pong atakihin ng fowl. Okay po. If you have questions, huwag po tayong mahihiyang ilagay ang mga tanong ninyo dito sa ating chat box or sa ating comment section sa FB at YouTube. Okay, so sa susunod po nating speaker, siya po ay isang entomologist at university researcher dito din po sa NCPC. At ang kanyang topic ngayong umaga ay patungkol sa modeling and remote sensing ng fowl infestation. Palakpakan po natin virtually si Mr. Gideon Aris Borgonyo. Mr. Gideon?
Thank you very much, Joy. Magandang umaga po sa lahat, no? Joy, pwedeng pa-enable ng screen sharing, please. Thank you.
Okay, so Miss Roma, Miss Charlotte, maaari po bang pa-enable si Mr. Gideon for screen sharing? Thank you. Ayan po, habang inaayos pa ng ating speaker ang kanyang pag-screen share, paalala po na ang pagbibigay ng certificate ay towards the end po ng ating webinar. Salamat po.
Ayan. Kita na po ba yung first slide, yung title page? Ate Joy? Nakamute ka, Ate Joy. Kita na po ba?
Yes po, Sir Gideon. Sorry.
Sige. Thank you po. So magandang umaga po muli sa lahat, no. So ang ang nai-assign po sa aking paksa po ngayon ay tungkol po sa modeling and remote sensing ng fall armyworm infestation sa corn. So pero bago po ang lahat, nais ko lang pong ipabatid na ang mga resulta po ng ang mga ibabahagi ko po ngayon ay mga pangunahing resulta po ng mga kasalukuyan po naming mga kinakandak na mga pananaliksik na pinondohan po ng DOST Guard na may pamagat na Development of Early Warning System Against Fall Armyworm through Phenology and Distribution Modeling, and isa pa po yung RETRAP or Remote Monitoring of Transboundary Plant Pests na pinondahan po ng DA-BAR. So maraming salamat po sa dalawang ahensya na ito na sa pagbabahagi po ng kanilang mga ng pondo para sa proyekto na ito. Okay. So dahil po ang mga ibabahagi ko po ngayon ng mga teknolohiya ay parang tools po for insect pest forecasting, parang papasadahan ko lang po muna ng konti yung tungkol sa insect pest forecasting, no. So, ang insect pest forecasting po ay prediction of pest incidents or outbreak based on biological, meteorological, and other physical factors. So, para po itong parang weather forecast po, no, parang marami po tayong mga tinitingnan factors para makita po natin yung yung trend and yung trend in space and in time ng natin, ng ating mga peste or ng ating mga insekto. Okay. So, isa po sa mga kadahilanan kung ba't po natin ginagawa nito ay dahil ang mga early warnings and forecast po base sa mga biophysical na methods ay nagpo-provide po ng lead time para ma-manage po natin yung impending pest attacks, and para ma-minimize po natin yung crop loss, ma-optimize natin yung pest control natin, and ma-reduce po natin yung cost of production. And another thing is that changing climatic conditions ay nakaka-apekto din po sa dynamics ng pest population natin. So meron po itong mga direct effects sa insekto mismo, and may indirect effects na through sa host ng peste. So nababago yung behavior and yung physiology ng natin, no, insekto. And ayun, and of course yung other yung other mga competitors niya, yung mga host plants and natural enemies. So yun po. Okay. So ano po ba yung mga kino-consider natin sa pag-model, no? So una po yung biology and or life history ng insekto. So dito po kino-consider po natin yung duration per stage niya. So kanina po na-discuss po ni Ma'am Selly yung life cycle ng fall armyworm, no? Saka yung mga fecundity or mortality, survival, host plant consumption rate, habitat carrying capacity, etc. So ito po ay pinapasok natin doon sa model para somehow matansya natin kung ano yung maaari niyang maging trend, no, sa ating farm level na setting. So ganun din po, yung isa din po sa mga factors na tinitingnan natin ay yung phenology. So yung epekto po ng temperatura or nung iba't ibang climatic condition sa development po, sa growth and development ng insekto. Okay. So ngayon, ito po yung parang ano natin, no, parang yung framework natin na sinusunod sa pagbibigay po para makapagbigay po ng advisory, no. So una, syempre titingnan muna natin yung status ng peste ng insekto through surveillance. Then iraran po natin to sa mga population and distribution models, and saka po tayo magbibigay ng advisory. So ito po yung parang general framework lang po ng NCPC advisory. So forecast advisory. Okay. So dumako na po tayo dun sa mga sa mga teknolohiya po, no. So una po sa yung FAO distribution modeling. So para po bawasan po yung potential impact ng fall armyworm, parang initial steps ng IPM should involve a surveillance system with some degree of accuracy. So pag may idea na po tayo ng preferred habitat and timing of occurrence ng different stages ng pest, maaari na po nating makapag-conduct effectively and efficiently ng monitoring activities, and makapag-schedule po tayo ng efficiently ng control measures. So yun nga, nabanggit din kanina ni Ma'am Selina, in 3 years FAO has spread from Asia to Africa, no. So ito po yung parang actual na distribution ng fall armyworm hanggang as of 2019, no. So ayan, ito po ay nakita na sa mga models natin, no, na ginawa nung previously pa. So ito parang ito ay climate suitability ng FAO na ginawa po ni Duplessis et al. Using Climex, and ito naman po ginawa ni Early et al. Using SDM. So ito pa is suitability map ng fall armyworm. So ngayon po sa project po natin sa NCPC, tinry po natin na parang i-downscale yung suitability maps, mga katulad nito sa Pilipinas. So what we did, ito po, no. So yung prediction po ng potential distribution ng FAO through ecological niche modeling. So first, yung presence records po ng FAO were collected from biodiversity databases such as GBIF, CABI, and IPCC, as well as yung published papers po and pest reports, and nakakuha po tayo ng 1,489 distinct records ng fall armyworm po, no, worldwide. And of course, dahil po meron na rin pong FAO noon sa Pilipinas nung nagsimula po yung project. So yung mga local data po from RCPCs and LGUs ay ginamit din po natin. So we used 6 environmental predictors, such as namely temperature seasonality, mean temperature of warmest quarter, annual precipitation of driest quarter, elevation and land cover, to develop yung model po, no, o yung potential distribution map. So ito po yung preliminary result, no, based po ito sa dun lang sa climatic records lang po, no. So ito po ay na-generate using MaxN 3.14 based on 453 global occurrences. Ito po yung mga permanent populations na and yung nabanggit ko po kanina na selected environmental predictors. Okay. So sa po, yung habitat suitability po ng FAO, so nakita po natin dito na yung may 97% po ng land area ng Pilipinas ay suitable po with predicted value of more than 0.2. So yung mga values po na more than 0.2 ay suitable na po for fall armyworm development. So pero yung high suitability threshold po with values na more than 0.6 ay na-observe po. Ito po yung mga mga dilaw hanggang pula na kulay ay observed po sa Luzon, buong Luzon except Palawan, sa Western and Central Visayas and Northern Mindanao. Okay. So yung AUC values po, no, so from 0.5 to better than random and to 1 or perfect prediction. So yung AUC values po na nakuha natin dito ay 0.835 and 0.827 for training and test data respectively. So ito lang po, sinasabi lang po dito na maganda po yung performance nung maganda yung performance ng model, no. Okay. So the three most significant environmental predictors based on permutation importance are ito po yung tatlo: temperature, seasonality, annual precipitation, mean temperature of warmest quarter. So based on variable response curves, the optimal temperature ranges from 25 degrees Celsius to 33 degrees Celsius, while optimal and annual precipitation ranges from 500 mm to 1,600 mm. So yan po yung mga parang main na predictors niya. So kung ganyan po yung sa lugar, yung condition sa lugar ay high, medyo mataas po yung suitability natin, no. Okay, so dumako naman po tayo sa spatial, no, sa temporal, no, sa population modeling. So basically ito po yung parang yung life cycle ng fall armyworm na nakikita natin. So ngayon sa model po, pag minodel na po natin ito, ganito po yung itsura niya, no. So ito po ang tinatawag na stock flow diagram. So ito po ay ginawa sa Stella software. So basically parang ginagaya lang po nitong Stella model yung ilan sa mga characteristics ng development ng FAO para po somehow makapag-predict ng future population niya, no. So dito po sa mga ilang parts po ng Stella model natin, no. So dito po kina-calculate po natin yung accumulation ng degree days o ng tungkol po ito sa temperature, no. So yung output po dito, pumapasok po dito sa module na to na naman po, nagko-compute naman po kung gaano katagal gaano kabilis o gaano katagal yung magiging development per stage ng fall armyworm. So ito po ay naka-input naman dito na sa main po natin na life cycle model. Okay. So basically po, sinisimulate po natin yung timing ng occurrence, yung density, and number of generations po ng pest per unit time base po nga sa climate and climatic temperature for sa required temperature for development. So yung temperature nga po pala, no, kinukuha po natin ito, parang fino-forecast din po natin yung temperature using ibang program naman po or ibang source po yung pang-forecast po natin ng temperature, tapos yun po yung ginagamit natin na input na model para somehow mag-jive po yung parang medyo mas malapit po yung mga predictions po natin, no? Okay. So ito po isang example sa comparison na observed and simulated data ng male fall armyworm po sa Batangas. So as you can see, so halos nagtutugma po, no, yung pula po yung pulang line po yung simulated, yung blue po yung actual na po natin, no, catch. So as you can see po, somehow nagtutugma yung peak and yung population niya, no. So yun lang po dito sa natin, dito sa medyo detailed na So we tried na, so ang po kasi sana ay ang tawag dito, yung framework sana ay sa field ay magkolekta ng male armyworm, and yun yung gagamitin, yung monitoring data na yun ang gagamitin to feed yung model para ma-predict yung yung future na population. So dito po sa initial, nag-try po natin gamitin yung initial population na 1,070 male moths. So parang from August 7 to 22 na collection po ito, no? So in-input natin ito sa model, and ito na po yung resulta sa sa graph na to. Yun nga lang, kung makikita nyo po, sakto naman po yung yung pag-rise ng population, parang halos sabay, no? Yung simulated, yung blue, yung orange, yung actual po. Kaya lang, kung mapapansin nyo, mas madami yung simulated kaysa dun sa observe. Kaya lang kasi, ang natin dito, parang dun sa site kasi natin ay mataas yung farmer cooperator natin ay mataas magbomba ng insecticide. So, medyo mas mababa yung populasyon na na-observe natin. Pero, basically, ito yung potential niya, no? Na pwede kang maka-observe ng 2,121 na male moths dun sa specific na period na ito. Okay. So, ayun. So, basically, ang target po target na users po nito usually ay mga po natin, no, mga nasa LGU po natin, no, nasa mga RCPCs, no. So ayun po. So currently po vina-validate and kinakalibrate pa po natin yung model, no, before po natin i-deploy. So ayun. Okay, so ngayon dako naman po tayo sa remote sensing po. Okay. So, ito po, parang produkto po ito ng natin sa retrap or remote monitoring of transboundary plant pest na project po ng DEBAR, no. So, ito po yung basic na flowchart natin, no, sa monitor or sa remote sensing, no. So first, we do aerial and ground survey. So we use UAV or unmanned aerial vehicle, or mas tinatawag din na remotely piloted aircraft systems or RPAS, mounted with MicaSense Red Edge MX, and we also use yung DJI Phantom for multispectral. Okay. So then yung image po na nakaka-capture natin sa field, so over cornfields, ay pinapadaan po natin sa photogrammetry and image classification na process where we use Agisoft Metashape Professional and QGIS 3.16. Excuse me lang po. Okay, then we do yung ground validation, or actually kasabay naman po ng aerial and ground survey yung ground validation, kaya nga lang yung comparison ay dito po nagaganap sa stage na to. Then we do stat analysis po, parang pang-comparison po ng ground and ng aerial survey. Okay, so lang po, no, konting background lang po. So healthy vegetation absorbs more red and blue light and reflects more near infrared or NIR and green light compared to other wavelengths. So the reflection of corn damaged by pests is higher than that of healthy corn in green and red band, and it is lower than that of healthy corn in NIR band. So sa study po ni Mingsheng et al., armyworm damaged corn produced higher reflectance values in the visible spectrum than healthy corn plants. Sa study naman ni Erickson, defoliated corn produces higher reflectance, thus an incremental relationship between reflectance and damage. So ito po yung basis natin, no, sa pagtingin po or sa paggamit po ng remote sensing sa fall armyworm po, no, sa corn. So ayan, so we conducted baseline analysis on the response of corn spectral index in relation to foul damage as affected by different insecticide treatments. So tiningnan po natin efficacy ng 7 organic, and 15 synthetic insecticides with conditional registration sa BAPS and sa FPA. And kinest po ito no, sa fall armyworm on a hybrid white corn in CES UPLB. So following standard bioefficacy trial protocol. So ito po ay kinonduct ni scientist Mario Navacero and Ms. Karen P. Ardes sa isang separate na research project. So while kinonduct po nila yung trial po no, yung nagpalipad po tayo doon ng drone, so para po mag-capture ng images. So okay, so nakakita po tayo ng significant differences among damages of fowl larvae on leaves. So these data were used to analyze if the extent of leaf damage caused by fowl influenced the spectral response of corn vegetation. So kumuha po tayo ng images during 1833 and 50 days after planting, tapos pinrocess nga po ito natin sa Agisoft and sa QGIS. Okay, so nag-conduct po tayo ng zonal statistics to extract po yung average NDVI and canopy para sa isang plot. Okay, so yan po. Okay, so significant differences in NDVI and canopy cover in corn treated with organic insecticides were observed in multispectral data taken during 50 DAP. Okay, so yung highest NDVI po ay makita po natin sa mga plots na treated with 0.46% matrine PS with mean of 0.47. And the lowest in 49% potassiums, salt of fatty acids with mean of 0.40. Okay. So yan po no, kita po natin yung so yung untreated control o yung parang mas yung walang mga spray, halos kapantay niya lang to no, itong mga part na to no. So dito yung matataas yung NDVI no. So ayun, consistent po siya sa canopy cover means with 0.6 matrine, PS having 21.69 square meters na parang halos kompleto na yun yung foliage no? Versus 18.01 square meters in 49% potassium salt of fatty acids. So tinitingnan lang po natin dito yung yung range po ng NDVI and yung canopy cover. So sa canopy cover po, makita po natin dito yung range ng quote-unquote defoliation ng fall armyworm. Okay, so NDVI and canopy cover are positively correlated during 18, 33, and 50 DAP. And foul damage rating was inversely related to NDVI at 33 and 50 DAP. So, yun po yung yung resulta natin dun sa mga buffs na pesticides. So, ito naman yung sa FPA. Ito naman yung sa mga synthetic na pesticides. Okay. So, mean NDVI of synthetic insecticide treated plots were significantly different during 33 and 50 DAP. So, at 33 DAP po, yung chlorantraniliprol recorded the highest NDVI while untreated control had the lowest. So, ito po, kita natin dito. And during 50 DAP, 8 AIs fit in the highest group of means, which is from 0.49 to 0.50, while 3 others are comparable with untreated control fell on the lowest group. Okay. So, dito banda, dito banda yung mga natin, mga mabababang NDVI. Dito yung matataas. Okay, so canopy cover was not affected by the treatments but showed positive correlation with NDVI in all stages. So during 33 and 50 DAP, foul damage rating revealed strong negative correlation with NDVI. And canopy cover also was inversely related to foul damage rating at 33 DAP and 50 DAP. Okay, So, moderate to strong negative correlation between NDVI and foul damage rating were observed in the 2 insecticide trials in study. So, the results of our study then suggest that NDVI can be used as a tool to assess the level of foul damage in corn at least during around 33 and 50 DAP. So, nagko-conduct pa po kami ng mas detalyadong study po, no, tungkol dito para malaman po natin kung ano pa yung iba't ibang stages ng corn ang sensitive or saan pa mas sensitive yung mga sensors natin sa iba't ibang stages ng corn, no, with foul damage. Okay. So, ito po, nakabuo na po tayo somehow ng parang manual. So, sa remote monitoring, no? So, it includes workflow sa image data acquisition, sa photogrammetry, sa image classification and analysis. So ang subject po nito ay detection and assessment of foul damage in corn through estimation of vegetation and spectral values and yung coverage po, no? Kasama rin po dito yung ayan. So, yun lang po. This is designed to be used by technical personnel in the regions or LGUs para ma-ano po natin. So, para either ma-detect, ma-monitor, and ma-assess po yung extent ng damage ng foul. So, ito po ay na-deploy namin sa DARCPC 3 and sa yung kasama po yung corn program 3. So, ayun po. So, ito na po, I think, ayan, tama. Ito na nga yung last slide ko. So, salamat po ng marami sa inyong pakikinig.
Ayan, thank you, Sir Gids. So, meron na po pala tayong RIT-trap for monitoring and assessing foul damage sa mais. Thank you, Sir Gids. Okay po. Para po sa mga humihingi ng copy ng presentations ng ating mga resource speakers, maaari nyo pong balikan ang webinar na ito, recorded webinar na ito sa ating Facebook page, UPLB CAPS National Crop Protection Center, at saka sa ating pong YouTube channel, National Crop Protection Center UP Los Baños. Ayan, okay? So, sa sunod po nating resource speaker, siya po ay ang ating Associate Dean for Research and Extension sa College of Agriculture and Food Science. Siya po ay UP Scientist 3 from the Institute of Weed Science, Entomology and Plant Pathology. So, ipapasalamat po tayo na kahit busy si ma'am, ay napagbigyan po tayo na maging bahagi siya ng webinar na ito. She will discuss entomopathogenic nematodes as biological control agents against fall armyworm. Ang ating pong ikatlong speaker ay walang iba kundi si Dr. Barbara Kawili. Ma'am Bambi.
Maraming salamat, Joy. So let me share my screen. Lang ha. Okay. Kita niyo na ang aking screen?
Yes, ma'am.
Okay.
Malaki po.
So magandang umaga po sa lahat ng mga participants sa NCPC webinar series on the management of fall armyworm. So I will be sharing our work on entomopathogenic nematodes, particularly ang aming pag-aaral sa posibleng gamit nito para ma-manage ang fall armyworm na kasalukuyang seryosong problema sa maisan. Kasama ko po sa paghanda sa talk na ito si Ms. Emerald Flor A. Felicitas, ang aming University Research Associate, at si Assistant Professor Romnick Latina, a Faculty of Plant Pathology at the Institute of Weed Science, Entomology, and Plant Pathology sa College of Agriculture and Food Science, UP Los Baños. So just to give you an overview on what to expect in this short talk, ito po ang aking outline. So magbibigay po ako ng background on entomopathogenic nematodes para ma-familiarize po kayo sa biological control agent na ito. Pangalawa, ay aking ibabahagi kung ano ang mga insekto ang ginamitan na ng EPN. Pagkatapos po nito, ay i-share ko sa inyo ang aming journey sa IWEP on EPN research at kung sino-sino pa ang nananaliksik on EPN dito sa Pilipinas. And lastly, we will be sharing with you our work on EPN for FAO management. Ang gamit ng EPN as biological control agent started when it was discovered in the 1920s. Their commercialization as biopesticide in the 1980s, and this was accompanied and followed by an exponential growth in research on their application, biology, ecology, followed by a further expansion in more basic research areas since the mid-2000s. No? Maliit lang po ang EPN, but they can be seen by the naked eye. Ang nakikita niyo pong video ay isang water droplet where hundreds of infective juveniles were trapped. Depending on the species, the IJs range in size from 0.3 to 10 millimeter, and they can be more or less cylindrical. Ang katagang entomopathogenic nematode ay nagmula sa salitang Greko na entomos, meaning insects, path, meaning disease, and guenos, meaning producing. So ang mga EPN ay a group of nematodes which have the ability to cause disease in insects by suppressing their immune system. So may dalawang kondisyones para makonsider ang isang nematode na EPN. So remember kasi mayroong plant pathogenic nematode. So EPN must rapidly kill their insect hosts with the aid of bacterial partners and must pass on the associated bacteria to future EPN generations. So EPN po are classified in the families Heterorhabditidae and Steinernematidae that share a number of characteristics. The family Heterorhabditidae comprises only one genus, yung Heterorhabditis, with Heterorhabditis bacteriophora as the type species. So may 21 described species under this genera. Okay. Yung Steinernematidae naman comprises 2 genera, and Steinernema ang type genus with 91 described species, and Neosteinernema with only 1 species. Several species of nematodes in the genus Ocheus in the family Rhabditidae, particularly those under the Insectivora group, also met or meet the criteria to be categorized as EPNs. So some Oceus species appear to be associated with only 1 species of bacterial symbionts, while other members of the genus are associated with multiple bacterial species. So however, these species are not as well characterized ecologically and are not yet used in biological control applications. So as I've mentioned earlier, EPNs have mutualism with bacteria or bacterium. So all species of Heterorhabditis have symbiotic associations with Photorhabdous species, while Steinernema have mutualistic associations with Caenorhabdous. So Photorhabdous and Caenorhabdous colonize a particular site in the gut of the IJ stage of their nematode host, as you can see in this figure as green bacteria. Makikita na ang mga bacteria ay located just posterior to the pharynx of the nematode. So however, it is clear that Photorhabdous bacteria occupy a substantial fraction of the nematode gut, while Caenorhabdous appear to be localized within a vesicle. Meanwhile, Oceus, depending on the species, can be associated with Bacillus cereus, Serratia marcescens, or Ochrobactrum tripisi. So meron pa pong ibang bacterium na na-identified associated with Oceus. So saan po mayroong EPN? So sana po nakikita nyo na malinaw ang global distribution map Ang EPN ay indicated by the red dots. Ito ay matatagpuan lahat ng kontinente. Except, ano po ito? Antarctica. Okay, so siguro napakaginaw nga po doon, no? But here, meron po tayong dot here in the Philippines, but this has to be updated since may mga reports na po on the presence of EPN in Visayas and Mindanao. So only Luzon lang po ang merong dot dito sa mapa na ito. So this is a very, very recent publication. So 2021 po ito.
So ang una natin i-decide.
So we can understand how EPN cause a disease in insect by looking into its life cycle. So yung free living or foraging stage is the infective juvenile or the IJ. So to locate a potential host, IJs employ various dispersal and foraging behavior which are a key component in their ecology and their use in biological control. Halimbawa, ang Steinernema carpocapsae ay isang ambusher or a sit and wait strategies. No, they tend to stay near the soil surface where specialized foraging behaviors such as yung nictation at saka jumping facilitate infection of mobile hosts. Sa kabilang dako, mayroong EPN species gaya ng Steinernema glacieri at Heterorhabditis bacteriophora na bibong-bibo. No, they are widely searching foragers, kaya ang tawag sa kanila ay cruisers. So these EPN distribute themselves actively throughout the soil profile and are well adapted to infecting less mobile hosts. Okay. So once they find a susceptible host, they will enter the host through their natural openings. So some species could inflict wound, and once inside the host, IJs may overcome or evade the host immune response by shedding off the second stage juvenile cuticle, depositing de novo produced or host sequestered immune factors as a camouflage, interfering with the host immune system by secreting putative proteins and releasing proteases. So yung both Sinorhabdus and Photorhabdus symbionts play complementary roles in overcoming the insect defenses and actively suppressing the immune response. They also produce and release several toxins lethal to the insect host, as well as antibiotics to prevent secondary infection of the cadaver by other pathogens or scavengers. So yung bacteria, will multiply, in the nutrient-rich hemolymph, and yung infective juveniles recover from their arrested stage and start feeding on multiplying bacteria and disintegrated host tissues. So isang pagkakaiba ng Steinernematids at Heterorhabditids ay ang kanilang mode of reproduction. For example, in Heterorhabditids, nematodes, the first generation individuals are produced by self-fertile hermaphrodites. So meron silang hermaphroditic stage, but subsequently, ito pala yan. And so subsequently, yung magpuproduce sila ng generation of individuals na males and females. While in Steinernematic nematodes, okay, but with an exemption of one species, all generations are produced by cross-fertilization involving males and females. So ayun yung amphimictic mode of reproduction. So depending on availability of food resource, both this group of nematodes generally complete 2 to 3 generations within insect cadaver and emerge as infective juveniles to seek new hosts. And then the cycle continues. Okay. So EPN has been used as biological control agent in various crop groups such as small fruits, so orchards, corn, vegetables, tuber crops as well as under greenhouse conditions. Ginagamit rin ng EPN sa pagsugpo ng insekto na umaatake sa mushroom. EPN can infect a number of insect species under the order Coleoptera, Diptera, Lepidoptera, Orthoptera, and Thysanoptera. Okay, but of course, they exhibit specificity. Okay. So marami ng commercialized EPN-based formulation sa Africa, sa Asia, Australia, Europe, North and South America. Gayunpaman, sa aking pagkakaalam, ay wala pa po tayong local EPN na commercialized. So 5 Heterorhabditis species po ang commercialized na at 8 naman for Steinernema. So, ngayon naman po ay babahagi ko ang aming journey on EPN research sa IWEB. Okay. Noong 2012, our project on diversity and biological control potential of EPN in their bacterial symbiosis against insect pests of bioethanol crops was funded by DA-BAR. So, kasama ko po dito si Sir Nick Latina at si Dr. Joey Arahay. So, in this project, we isolated 7 populations of EPN from Batangas, Bukidnon, Laguna, and South Cotabato. Okay, so we identified them as Steinernema abasi, Steinernema minutum, Steinernema tami, at Heterorhabditis indica. So based on our bioassay, Steinernema abasi at Heterorhabditis indica are good candidates for the management of Asian corn borer, corn earworm, and the common cutworm. Okay? Ang aming pong resulta ay aming i-publish sa Journal of Nematology. So ang aming research on EPN ay nakapagsuporta ng mga undergraduate at graduate students na makikita nyo sa mga sumusunod na slides. So sa kasalukuyan po, may research po kami na pinondahan ng DOST Picard on biological control of fall armyworm using entomopathogens kung saan ang project leader namin ay si scientist Celi Navasero. Isa po ang EPN sa biological control agent na pinag-aaralan sa project na ito. So ito po yung mga research on EPN ng aming students na nagawa na. So we try to look for an alternative insect host for Galleria melonella kasi ito po yung standard na ginagamit sa pag-mastery ng EPN sa ibang bansa. And these results indicate na yung 13-day-old Furnacalis larva is the most suitable host for in vivo mass production of Heterorhabditis indica PBCB. So another study po ay nakapag-isolate kami ng another EPN population sa Zamboanga City. So yung molecular and morphological analysis revealed that this EPN belongs to Steinernema carpocapsae species complex. So hindi pa po namin natumbok kung anong species siya based on molecular analysis. So baka po siya ay novel species. And yung bioassay studies show that this particular population was pathogenic to the larvae of Stringia forticalis, Tenebrio molitor, Rutella silostella, and Helicoverpa armigera. So additional Heterorhabditis indica populations from Palawan, Surigao del Sur, was also isolated and compared with the Batangas, yung una po naming nakuhang Heterorhabditis indica using morphometrics and partial cytochrome oxidase subunit 1 gene sequences. So yung pathogenicity and virulence ay nakita namin sa Asian corn borer, sa mealworm, at also sa wax moth. So Galleria po siya but hindi Melonella. And intraspecific differences was observed. So most virulent po among these Heterorhabditis indica ay ang BSDS, okay? And yung sa Tenebrio molitor. But for Ostrinia fornicalis, yung Heterorhabditis indica PBCB ang most pathogenic. So another EPN population was isolated from Barangay Carolina, Canavid, Eastern Samar, and it was tested for pathogenicity against red palm weevil. So this was identified again as Heterorhabditis indica using both CO1 and ITS barcode regions, and Photorhabdus luminescens po ang associated bacterium. So using field population of palm weevils, nakita po namin na nakita ni Manilin na this particular population was able to kill the insect, but siguro napakalaki nga noong insekto, so matagal bago mag-emerge yung infected juveniles. Then kinalaunan na po is wala na pong infected juveniles na nag-emerge from them. So maybe yung immunity ng insekto na ito had suppressed yung multiplication of that EPN. So meron din pong mga estudyante na nag-aral on the entomopathogenic bacteria associated with EPN. So tiningnan po ang effect nito sa plant pathogenic fungi. So yung cell-free filtrates of Photorhabdus luminescens and Sinorhabdus indica isolates were tested against Rhizoctonia solani. And nakita yung high suppression sa growth of this particular fungus. Okay. The same was observed on Photorhabdus luminescens strain, cell-free filtrates against another 3 fungal species. And yung result po ni Paulo and Sam were published recently in the Egyptian Journal of Biocontrol, Egyptian Journal of Biological Pest Control. Okay. So tiningnan din po ang effect ng APB on plant parasitic nematodes, and nakita rin po na merong itong nematicidal activity at 24 hours post-exposure. Okay. Then meron din pong work on suppression, kung paano pag-suppress ang gall formation sa plant parasitic nematodes using Steinernema at saka Heterorhabditis indica. So, sino-sino po ang iba pang nagre-research ng EPN dito sa Philippines? So, according to my search po, mayroon pong nag-work sa BSU, si Dr. Gapasin. Okay? Si Manilin Alde po ay currently nasa BSU, so hopefully she will continue her work on EPN. So meron din po nag-work on MSU IIP, si Ma'am Dr. Nanette Hope Sumaya. So Dr. Nordaline Perdoche of Benguet State University is working on also in EPN, and I think they have several isolates of Oseus species. And meron din po akong nakita si Sir Dr. Pet Rowie Pascual of Cebu Technological University who worked on EPN. So alam ko po na marami pong attendees from other SUCs, and kindly email me if you have initiatives sa EPN studies na hindi ko po na-mention. So we are planning to establish a professional academic society for EPN enthusiasts. So now to share studies on EPN against FAO, we tested the pathogenicity of 4 local EPN based on percentage penetration and mortality. So using same IJ concentration, so makikita the percentage penetration of Heterorhabditis indica isolates range from 20.42 to 26.94%, was found to be significantly lower than that of Steinernema abasi, with 55.04%. Okay. So the following preliminary result may indicate the highly virulent character of the 3 Heterorhabditis indica isolates when compared to Steinernema abasi. Okay. And then, so mortality, in terms of mortality, okay, so we can see that the Heterorhabditis indica isolates exhibited significantly they cause significantly higher mortality to fall armyworm as compared to Steinernema abasi. Okay, so this trend was continuously observed until 48 hours post-infection. So at 48 hours post-infection, 100% mortality was observed in 2 Heterorhabditis indica isolates. Okay. So we also did pupil assay and examined the effect of EPN on adult eclosion rate of fall armyworm. So yung adult eclosion rates of fall armyworm pupa did not differ significantly among the EPN isolates. However, relative to control, your lowest adult emergence was observed in Heterorhabditis indica, PBCB, followed by Heterorhabditis indica MAP, and then Heterorhabditis indica BSDS, and lastly, Steinernema abasi and BLB. So this just showed na talagang mas virulent ang mga Heterorhabditis isolates namin than the Steinernema abasi we have. Okay. So we also look into the effect of cell-free filtrates of Sinorhabdus on larvae of fall armyworm. And cell-free culture of Sinorhabdus showed highest effectiveness at 100%. So puro po, meron pong 66.67% mortality on the 3rd instar larvae, while for 2nd instar larvae, na-observe po is 71.85% mortality. So our results demonstrated the potential of EPN and EPB against fall armyworm. We will now validate this under field conditions, and I would like to take this opportunity to invite collaborators for these small field trials. So with the support of USC and DA, hopefully we could develop EPN-based formulations as alternative approach for FAO management. So our research proposal po is currently being prepared. Again, those who are interested to collaborate are welcome. Okay, so ito po ang aking mga major references na ginamit dito sa presentation na ito. And maraming salamat po. Sa inyong pakikinig. Ay, ayaw po mag-on.
Maraming salamat, Ma'am Bambi.
Ayan po, makikita nyo po yung fall armyworm, lumalabas na po yung EPN. Salamat, Joy.
Okay, Ma'am. Maraming pong salamat, Ma'am Bambi, sa pag-share ng about sa EPN. Yung potential use po talaga nito sa fall armyworm. Okay po. Salamat po, Ma'am. So, paalala po sa ating mga attendees dito sa Zoom space at saka sa mga sumusubaybay po sa NCPC Facebook page at saka sa YouTube channel po natin. Makakatanggap po kayo ng e-certificate kung mag-fill out po tayo mamaya ng ating evaluation form. Ipa-flash po ito pagkatapos ng ating lahat ng ating mga speakers. Okay po, bago po matapos ng webinar. Okay, so nakatatlong speakers na po tayo. Kung kayo po ay ready na sa pang-apat na speaker natin, makiklik naman po ng ating heart react button. Okay, gising pa po ba tayo? Tuning nga po na siksik. Yan. Napakadaming impormasyon po ang ating matututunan ngayong araw. Ayan, salamat po. Okay, so our fourth speaker ay si Ms. Melissa Montecalvo to discuss about the potential entomopathogenic fungi against fall armyworm. So kanina na-discuss ni Ma'am Bambi ay EPN, ngayon naman po ay EPF. Okay, so ang ating pong speaker ay isang plant pathologist at university researcher dito din po sa NCPC. So bigyan po natin ng virtual clap si Miss Aiza. Miss Aiza.
Ang deteksyon ng harabas ng mais o yung fall armyworm sa Pilipinas simula noong June 2019 ay nag-udyok na manaliksik ng mga pamamaraan upang maiwasan ang pinsalang dulot nito. Ngayong umaga, akin pong ibabahagi sa inyo ang resulta ng aming pananaliksik sa potensyal ng mga kaibigang amag bilang biological control agents laban sa harabas ng mais. Magandang umaga po. Ako po si Melissa Montecalvo, isang researcher mula sa National Crop Protection Center. Akin pong tatalakayin ngayong umaga ang mga sumusunod na paksa, ang biological control na parte ng integrated pest management. Sa mga biological control agents po, atin pong tututukan ang mga kaibigang amag, kung paano ito nagdudulot ng impeksyon sa mga pesteng kulisap, pati ang mga bentahe at limitasyon ng paggamit nito. Akin din pong ibabahagi ang resulta ng aming mga pananaliksik gamit ang mga kaibigang amag laban sa harabas ng mais. Ang layunin po ng aking presentasyon ay para magbigay ng dagdag kaalaman patungkol sa mga kaibigang amag na mabisang pamuksa sa harabas ng mais. Alamin po natin ang epekto ng kaibigang amag sa iba't ibang yugto ng harabas, tulad ng itlog, ng uod, ng prepupa, at ng uod tulog. Dito po sa slide na ito ay ipinapakita yung mga components ng Integrated Pest Management o yung tinatawag nating IPM na isang konsepto at sistema ng epektibong pamamahala sa mga peste sa taniman. Isinasaalang-alang po dito ang mga available at yung mga practical na crop protection solutions o iba't ibang pamamaraan tulad ng pest monitoring, ng cultural methods, ng physical control, ng biological control, gamit po yung mga microbials, yung mga natural enemies natin, at yung chemical control, gamit po yung organic at yung mga sintetikong pestisidyo. Ito po ay magagamit natin upang maiwasan ang mapinsalang epekto ng mga peste at maprotektahan po ang mga kaibigang kulisap, ang tao at ang kapaligiran. Ang paggamit ng iba't ibang strategiya ay lubos na makakatulong upang maiwasan ang labis at maling paggamit ng mga pestisidyo. Ano po ba yung tinatawag nating biological control o paggamit ng mga tinatawag nating natural enemies sa pamamahala ng peste? Ang mga natural enemies ng pesteng kulisap ay tinatawag ding biological control agents, kung saan kabilang ang mga predators, ang mga parasitoids, at yung mga pathogens. Ang mga biological control agents po ay mga alternatibong pamamaraan na epektibo at ligtas gamitin. Nabanggit po natin kanina na ang pathogens ay biological control agents. Ito pong mga pathogens na ito ay maaari ding tawaging mga microbials o yung mga kaibigang mikrobyo o entomopathogens. Ano-ano po ba ang mga ito? Nariyan po ang bakterya, ang virus, ang amag, ang nematodes, na may iba't ibang pamamaraan sa pagdulot ng impeksyon sa mga pesteng kulisap. Ang mga microorganisms na po ito ay pumapatay at nakakaapekto sa paglaki ng iba't ibang pesteng kulisap at maaaring magdulot ng impeksyon sa marami o partikular na insekto, mites at ticks. Atin pong tututukan dito sa presentasyon ang mga kaibigang amag o yung tinatawag nating entomopathogenic fungi o yung EPF. Ang mga karaniwan po nating maririnig ay yung Boveria, Isaria, Hirsutella, Metarhizium at marami pa pong iba. Ang mga kaibigang amag ay madalas po na may broad host range o ibig sabihin po nito ay maraming naapektuhang uri ng mga kulisap. Ngunit paano po ba nagdudulot ng sakit ang mga kaibigang amag? Dito po sa larawan ay makikita natin kung paano ba nagdudulot ng impeksyon ang amag. Nag-uumpisa po ito sa pagdikit ng tinatawag nating conidia o yung binhi ng amag sa balat ng insekto. At kapag mainam ang kondisyon tulad ng mahalumigmig at katamtamang temperatura, ito pong binhi ay tutubo at papasok po yan sa balat ng insekto sa pamamagitan ng enzyme degradation at mechanical pressure. Kapag ang amag po ay nasa loob na ng katawan ng insekto, ay ginagamit po nito yung sustansya na nasa loob ng insekto upang mas mabisang makapagdulot ng sakit. At sa paglalapo ng impeksyon, lalabas yung amag sa balat ng insekto at kalaunan ay mababalutan na ito maaring yung kabuuan ng insekto o parte ng insekto. Matapos po nito ay magsisimulang bumuo ulit ng tinatawag na conidia o yung binhi ng amag na maaring kumalat at makahawa sa iba pang insekto. Ano po ba yung bentahe sa paggamit ng kaibigang amag? Una-una po sa lahat, ito po ay epektibo laban sa maraming pesteng kulisap tulad ng harabas, ng whiteflies, ng aphids, ng atangya at marami pa pong iba. Maaari po itong manatili at magparami sa taniman dahil likas po itong matatagpuan sa lupa at halaman at ito po ay nabubuhay sa halaman bilang endophyte. Ito po ay ligtas gamitin sa pananim at isang importanteng strategiya sa integrated pest management upang maiwasan yung tinatawag nating resistance development ng maling paggamit ng mga pestisidyo. Napaparami din po ito gamit ang mga murang sangkap tulad ng mais, ng bigas, palay, darak, ipa sa aseptic na kondisyon. Ito po ay madaling gamitin, i-spray o isabog sa taniman. Mag-spray lamang po kung hindi matindi ang sikat ng araw at magdagdag ng surfactant sa pagtimpla ng amag na magreresulta ng mas pantay at kalat na distribusyon. Importante rin po na kinakalog natin yung knapsack sprayer upang mahalo po yung binhi ng amag sa loob ng ating sprayer. Ano naman po yung limitasyon sa paggamit ng kaibigang amag? Una-una po sa lahat, ang epekto po nito ay hindi kasing bilis ng sintetikong pestisidyo. Base po sa aming pag-aaral, nagsisimulang mamatay mga 1 hanggang 2 araw matapos atakihin ng amag, ngunit ang kapansin-pansing dami ng namatay ay nakikita. Nagsisimula po ito ng mga 4 na araw. Kung babalikan po natin kung paano nagdudulot ng sakit ang amag sa pesteng kulisap, makikita din po natin na ang bisa ng amag ay naapektuhan ng temperatura, klima at halumigmig. Ang katamtamang temperatura at halumigmig ay kailangan po ng amag upang ito ay magdulot ng impeksyon. Ngayon naman po ay babahagi ko na sa inyo yung resulta ng aming mga pag-aaral sa laboratorio at sa field. Sinubukan po namin yung Metarhizium anisopliae at yung Boveria bassiana. At meron din po kaming isolate ng Metarhizium relayi na galing po sa harabas ng sibuyas. Nung nagsimula naman po kaming magkaroon ng mga field survey, nakakuha po kami ng harabas ng mais na nababalutan din po ng M. relayi. Kaya ito po ay sinubukan din namin laban sa harabas. Narito po ang tinatawag na mycosis o yung pagkamatay ng harabas ng mais dulot ng Boveria bassiana. Mapapansin po natin dito sa mga larawan na ang mga naapektuhan ng Boveria bassiana ay nababalutan ng puting amag. Tulad ng dito po sa uod tulog, at maging sa paru-paro ng harabas ng mais. Kaya ang Beauveria bassiana ay tinatawag din po na nagiging sanhi ng white muscardine disease. Ang Metarhizium anisopliae naman po ay tinatawag na green muscardine fungus. Bakit po? Sapagkat yung mga namatay na kulisap ay makikita nating nababalutan ng berdeng amag, katulad po ng nasa larawan. Ang mga nasa larawan po ay uod at prepupa ng harabas ng mais na nababalutan ng Metarhizium anisopliae. Sinubukan po namin ang Metarhizium anisopliae at Beauveria bassiana nung hindi pa po kami nakakakita na tawag nating indigenous na entomopathogenic fungus sa fall armyworm. Sinubukan po namin ang bisa nito sa itlog, sa uod, sa prepupa, maging sa uod tulog. Nakita po namin na yung itlog at yung uod ng harabas ng mais ay susceptible po sa Metarhizium anisopliae at Beauveria bassiana. Makikita po natin dito sa figure 1 na may ovicidal activity o nagkaroon po ng mas mababang pagpisa ng itlog ng pau. Gamit po yung 1 × 10⁹ conidia per ml ng amag. Dito naman po sa mga graphs na ito, makikita natin yung epekto ng Metarhizium anisopliae at Beauveria bassiana sa uod ng pau. Makikita po natin na dumarami yung namamatay na uod hanggang sa 10 araw. Yung impeksyon ay nagsimula 1 hanggang 2 araw matapos po itong masprayan, at yung mga early larval instars, particularly po yung first instar, yung pinakabatang instar or pinakabatang uod, ay napaka-susceptible po nito sa Metarhizium anisopliae at sa Beauveria bassiana. Yung Beauveria bassiana po ay nakita nating mas mabagsik siya kesa sa Metarhizium anisopliae. Base po dito, kung saan ang Beauveria bassiana ay nagdulot ng 97% mortality kumpara sa Metarhizium anisopliae na 61% lamang ang mortality sa first instar ng harabas. Ngunit, kung titignan naman po natin yung epekto nila sa ibang larval instars, makikita naman po natin na pareho naman yung kanilang epekto. Pareho po silang mabisa sa pagpatay sa mga larval instars. Dumako naman po tayo doon sa epekto nito sa prepupa at doon sa uod tulog. Gamit yung 1 × 10⁸ conidia per ml ng Metarhizium anisopliae at Beauveria bassiana, inalam po namin ang epekto nito sa prepupa at sa uod tulog. Nakita po namin na mababa yung mortality sa prepupa, kung saan meron lang 3% sa Beauveria bassiana at 20% dun sa Metarhizium anisopliae. Samantalang yung uod tulog naman ay hindi naapektuhan. Subalit yung mga paru-paro ay nagkaroon ng abnormalidad tulad ng mas maliit yung pakpak na maaaring makaapekto sa pagpaparami ng insekto. Hindi po nakakaapekto talaga yung mga kaibigang amag sa prepupa at sa uod tulog. Dahil po mas maikli yung tinatawag nating panahon upang magkaroon ng impeksyon at makapal at sclerotized yung balat ng uod tulog. Doon naman po sa katatapos namin na transboundary project na sinuportahan ng Department of Agriculture, Bureau of Agricultural Research, sinubukan po namin ang bisa ng sipit-sipit at ng kaibigang amag laban sa harabas ng mais. Nagtanim po kami ng IPB VAR 6 sa Pili Drive dito po sa UPLB. Naglagay po kami ng 22 earwigs at nag-spray po kami ng kaibigang amag. Ang kinuha po naming data dito ay yung damage rating, gamit po yung Davis scale At syempre, kinuha rin po namin yung yield data. Nakikita po natin dito sa graph na walang kaibahan yung treated at yung control dun po sa leaf damage at sa ear damage. Maaring dahil po sa mababa yung pest population noong kami po ay nag-experiment. Pero makikita po natin ang kaibahan dun sa tassel damage, kung saan mas napababa po yung damage sa tassel sa paggamit ng sipit-sipit at ng kaibigang amag. Mas mataas ang nakuha naming ani doon po sa may tinrit namin ng sipit-sipit at ng kaibigang amag kung ikukumpara ito doon sa walang treatment. Ngayon naman po ay dumako po tayo doon sa naging resulta ng aming eksperimento gamit po yung metarhizium relay. Meron po kaming mga uot ng FAO na nakolekta sa Quezon Province. Nakita po namin na ito po ay nababalutan ng amag at ito po ay dinala namin sa laboratorio at in-isolate po namin itong amag na ito. At nakita po namin na ito ay isang metarhizium relay base po sa kanyang cultural, morphological, at saka yung molecular characteristics. Sa artificial media, makikita po yung una ay puti at kalaunan ay nagiging olive green yung kanyang colonies. Under microscope naman po, makikita yung kanyang conidia na hyaline and ellipsoidal to cylindrical. Tulad po nung aming testing sa metarhizium anisopliate Boveria bassiana, tinry po namin itong metarhizium relay na ito sa iba't ibang yugto ng harabas ng mais, sa itlog, sa uod, sa prepupa at sa uod tulog. At nakita po namin na wala po itong epekto sa pagpisa ng itlog. Ngunit nakita po namin na yung mga uod na nagmula dun sa napisang itlog ay namatay na uod. At hindi na po ito naging paru-paro. Sa uod naman po, nakita po namin na yung umpisa ng impeksyon ay nagiging matigas yung uod. At kalaunan ito po ay unti-unting nababalutan ng amag, nag-umpisa pong puti, hanggang sa unti-unti itong nagiging bete. Maaring partial or complete yung mummification. At hindi po nababalutan yung ulo at saka yung anal segments. Dito po sa graphs na ito ay makikita naman natin yung epekto ng metarhizium relay galing sa FAO sa mga uod. Dito po sa figure 6, makikita po natin na yung mga uod from first hanggang 6th larval instars ay susceptible sa M-relay. Sa 5 days after treatment po, ay less than 20% yung mortality. Subalit, nung mas tumagal, naging 7 hanggang 10 days after treatment, mas dumami yung namatay dulot ng M-relay. Dito naman po sa figure 7, makikita po natin yung epekto ng iba't ibang konsentrasyon ng metarhizium relay. Kapag mas mataas yung ginamit nating conidial concentration, mas maraming namamatay. Ngunit pagdating naman ng 7 hanggang 10 days, ay halos pare-pareho na rin po yung effect ng mga conidial concentrations. Tinignan din po namin yung epekto nito sa prepupa at sa uod tulog. Doon sa prepupa, mas mababa po yung naging pupation o yung tinatawag nating pagiging uod tulog niya at yung pagiging paru-paro. Walang epekto sa uod tulog dahil nga po doon sa matigas yung balat ng uod tulog. Amin din po sinubukan ang bisa ng isang isolate ng metarhizium relay na galing sa harabas ng sibuyas. Base po sa aming mga experiments, ay nakita po namin na mabisa din itong metarhizium relay isolate na ito. Sa katunayan po, ito ay na-test na po namin sa fall armyworm, sa onion armyworm, at true armyworm. Kasi sa mga resulta ay masasabi nating nakakaapekto ang kaibigang amag sa iba't ibang yugto ng harabas ng mais. Nakita po natin yung epekto nito sa laboratorio at dun sa field experiment. Sa kasalukuyan, tuloy-tuloy po ang aming mga tests na ginagawa sa laboratorio, pati po sa field. At tinitignan din po namin yung tinatawag nating endophytic colonization nitong mga amag na ito at yung kanilang survival sa lupa. Kami po ay nagpapasalamat sa DOST Picard at sa Department of Agriculture, Bureau of Agricultural Research para po sa kanilang suporta upang maisagawa ito pong aming proyekto. Nais ko din pong magpasalamat sa UPLB at sa CAPS at sa akin pong mga kasamahan sa amin pong project team. Para po sa karagdagang impormasyon, maaari niyo po kaming makontak sa aming email account, ncpc.uplb@up.edu.ph at sa aming FB account, na UPLB CAPS National Crop Protection Center. Maraming salamat po at muli magandang araw.
Okay, maraming salamat po,
Ang
Ma'am
deteksyon ng harabas ng mais o yung fall armyworm.
Okay, maraming salamat po muli, Ma'am Aisa, sa pagbahagi ng inyo pong research regarding sa EPF. Okay po, so from microbials, tayo naman po ay dadako sa mga natural enemies ng harabas. So ano-ano nga po ba ang mga pwedeng gamitin natin na kaibigang kulisap sa pamamahala ng harabas? Ito po ang topic na i-discuss ng ating fifth speaker. Siya po ay entomologist at university researcher din dito sa NCPC. Siya po ay walang iba kundi si Miss Marie-Joy Beltran. Ma'am Marie?
Good morning, everyone. My name is Marie, and I will be your speaker for the topic. Biological control of fall armyworm using natural enemies in corn, particularly the pre-release evaluation procedure in the selection of natural enemies against fowl. So this is a 22-slide presentation, and this covers 3 major topics. The first discusses about some basic concepts with regards to biological control in general. The second describes the 3-step research protocol in evaluating natural enemies. And the third provides some take-home messages for today's topic. Let's start with the question, what is an effective biohand agent? So for those of you who took courses in biological control, or those who are interested in this topic and read a lot of articles about this, I know this is a very familiar question to you. This is a question that asks, what features or attributes make a biohand agent successful at controlling pest populations? Here you can see the parameters which are usually associated to effective biohand agents. And an alternative to this explain that effective biohand agents should have a host or prey searching behavior that enables them to locate habitually the target pest individuals, even they are in low pest densities. Okay, next slide. Let's go to expectation of control. Which of these images do you think will have a more chance of developing severe pest populations? And when you know that your farm is already having pest outbreaks, how do you bring down the population from outbreak to non-outbreak level? So biohand agents are not like pesticides. They do not provide an instant kill effect within 24 hours. Biohand agents, in particular insect natural enemies, are living organisms. They can move within your farm, away from your farm, and then back into your farm. So that pest control, which is a consequence of this movement, is usually explained in this context. So what I'm trying to point out here is that biohand agents have a more chance of successful control if they will be used to suppress or prevent the growth of populations. And by that I mean that the target pest population should be at low pest density. This slide shows you some natural enemies associated to corn in the Philippines. So because the crop that we want to protect against FAO is corn, then it follows that the biohand agents that we should screen against FAO should at least be attracted to or associated to corn. In here you see the egg parasitoids, the species of Trichogramma, the species of predatory earwigs. So I grabbed that from the work of Dr. Javier, particularly Uberella annulata, which is the focus of my presentation for today, the predatory green lacewings, as well as the predatory coccinellid beetles, and the Euconticana forcillata predator, which are the focus group of Dr. Adorado's study. So we identified firstly the life stage of fowl that would be targeted for control by our predator. We studied some aspects of the biology in the lab and the behavior of fowl in the field to achieve that. So in here you have high survival rates in the second instar, fifth instar, as well as in the sixth instar of fowl. Now we want to cross out fifth and sixth instars because in these stages you already have more injury or damage to the plant. So why not first instar? No, we don't want first instar because that stage had the highest mortality, and this is typical in insects where they are usually dying at a younger age. Therefore, the ideal stage to control is the second instar, and by second instar I mean yung 3 to 4 day old larvae. That's between late first instar to early second instar. Another reason why we do not want first instar is because aside from having the highest mortality rate, newly hatched first instars are capable of larval ballooning that allow them to leave the plant after release. And that those first instars that remained in the plant are also capable of movement within the plant. So this one is showing you preliminary data, but this also suggests that newly hatched first instars are capable of dispersing from the release point to the surrounding plants 24 hours after release. We can now proceed to step 2. So in here we use several parameters to evaluate if the prey relationship of our predator to fowl is functional. Another point is that I also added the concept of provision of alternative prey to the biohand agent, and I chose the cowpea aphids, which is a common pest of leguminous crops. So in here you see that we made the adult female earwigs choose between the different conditions of the same or different plant species in the lab. The decision to choose, however, is a little bit difficult to measure for this species because first, the adult stage is wingless, and second, we do not have the right equipment yet to study insect behavior. Anyway, this data show you that the adult female earwigs cannot discriminate between different conditions of the same and different plant species. Another data set also shows that female adult earwigs could not discriminate between infested and non-infested plants of the same species. This would mean it will be attracted to the plant even though it is not yet infested. And maybe that's good because you know na pupunta siya sa crop even though at low or close to zero pa yung pest density. This slide shows you some data on prey consumption of female adult earwigs. Again, the data sets show that female adult earwigs could not discriminate between different types of prey. So whatever we give it in the lab, kinakain niya. One way to explain this is because of starvation. We did not compare starved versus unstarved individuals. This slide shows a data set in the no-choice test in 1 hour and in 24 hours consumption. This is just to give you an idea how many prey it can consume within a period of time, of course inside the container. So let us now proceed to the next parameter. In here you see that our biohand agent has high total survival rates when they are fed with FAO only and with alternating FAO and cowpea aphids. You can also see here that total mortality is highest when they are fed with cowpea aphids alone, and that the total survival is only 0.63 or 63%. This information could be useful when designing conservation practices to enhance the earwigs population very early in the corn cropping season or even before the corn is grown. Now we proceed to the last parameter. In here you see that the provision of corn pollen enhances total egg production of adult female earwigs fed with either the control, which is the fish meal, or fowl larvae alone. This suggests that this species of earwigs is likely to be attracted to corn plant, particularly to the tassel, because of this additional resource. So fowl individuals that are infesting corn tassel are likely to be encountered by earwigs. We also did soil sampling activities in 2 different farm sites in Laguna to characterize local abundance of earwigs population at the start until the end of corn cropping season. And in here you see that the total number of earwigs individuals are higher at certain age of the crop, particularly in the latter part or near end ng cropping period. And this supports or this corroborates with yung lab results namin na earwigs are most likely attracted sa corn because of its attraction to corn pollen. Now we go to Trichogramma. In the case of Trichogramma, we are still in the step 1. So yung verification of the species status. So what we did in here is that we studied first yung mode of reproduction ng species to check if it's sexual or asexually reproducing. After confirming the sexual, we did video recordings to characterize yung mating behavior. These data are helpful when we submit our samples for species confirmation sa taxonomist. We also did some simple experiments on percent parasitism, but this is not yet conclusive because ACB is not yet included in here. I would like to recognize the work of Dr. Javier and Dr. Gonzalez in predatory earwigs and Trichogramma. So, together with other local agencies, they have contributed a lot in the development of mass clearing and release protocol of these Biohand agents in corn, but against ACB. So if any one of you guys would like to know the reading protocol of these Biohand agents, just let us know and we can provide this to you. As for the release protocol of FAO, we can provide this to you maybe early next year, hopefully after ng extension of project. So let's go back to the image showing you yung different cropping patterns ng corn. What biocon agent do you think would persist in each of these type of cropping pattern? So this is the focus of our study next year. We will do field surveys to characterize what species of Trichogramma is more abundant if corn is planted next to vegetable or if it is planted alone. And this would be helpful when we design a release protocol for each biocon agent against FAO and corn, hopefully next year. Okay, this is the last slide. These are the take-home messages for you guys. So what we know about the pests. So first, we know that many are dying at a very young instar. Second, capable of larval ballooning. And third, capable of dispersing within the plant and between the plants. So what about the predator? First seems to be polyphagous. Second, has higher survival in FAO than in cowpea aphids. And third, also pollen feeder and probably for reproduction. Fourth, seems to arrive late in the cropping season. So I would like to acknowledge DOST Picard for funding this project, and of course our project leader, Dr. Adorada, and as well as all my staff at NCPC PLB. So thank you.
Ayan, salamat po, Ma'am Marie. Okay, so gusto po natin i-acknowledge ang 207 participants dito sa Zoom space. Meron din po tayong mga kasamahan na nakasubaybay sa YouTube na 100 plus, tapos sa FB din po. Salamat po sa lahat ng nanonood at nagpa-participate dito sa ating webinar na ito. Okay po, so mamaya po natin i-entertain ang inyong pong mga questions. Okay, sa atin pong pang-anim na speaker ngayong umaga, siya po ay si Ms. Karen Ardes upang ibahagi ang impormasyon sa Insecticide Resistance Management. Isa din po siyang entomologist at university researcher dito sa NCPC. Hindi na po natin patatagalin pa. Tawagin na po natin si Ms. Karen. Ms. Karen?
Hello po. Dinig po ba ako?
Yes po, Ms. Karen.
Dinig ako. Okay. Thank you. Marami pong magandang araw po sa lahat po ng mga nanonood po ngayon. Napakadami po nating participants. Maraming salamat din sa pag-imbita sa akin sa webinar na ito. So I will start my presentation. Paki-let po akong mag-share ng screen. Today, I will share with you the basics of insecticide resistance management with emphasis to fall armyworm as well as current to local growers practice and recommendation to delay insecticide resistance in growing corn. So these are the following topics that will be tackled. This includes the definition of insecticide resistance, concept about IRM, the proposed IRM framework, which is important in delaying insecticide resistance, yung mga validated insecticides na part po nung ongoing project namin na pwede na po namin i-recommend sa growers ng corn. So, to start with, I want to share with you a video that tackles the importance of IRM, what induces insecticide resistance, and how to delay insecticide resistance.
CropLife International and the Insecticide Resistance Action Committee explain how to combat insecticide resistance. This farmer is called James. He loves his job and is very proud of his produce. To avoid insect damage to his crops, James has always used the same insecticide and never had a problem. This year, James is worried because his crops are infested and spraying his fields does not kill many of the insects. If this continues, the whole harvest could be destroyed. James can't understand why the insecticide that worked so well before is not working so well now. An insecticide loses its effect because the insects have developed resistance to it. In any population of insects, there is genetic variability. The variability may give some insects a natural protection from this insecticide. If the same insecticide is always used, only insects that have this advantage survive. These resistant insects reproduce and pass on their advantage. Over time, this selection process fills the fields with resistant insects that are not affected by the insecticide. Luckily, there are other insecticides that have different modes of action. This means they attack the insects in different ways. Great, but how can we stop the process repeating and new types of resistance developing? Researchers carried out studies that show that by spraying insecticides with different modes of action in rotation throughout the crop growing season, the insects are controlled and the chance of resistance developing is greatly reduced. James can find information about what mode of action an insecticide uses printed on many bottles, online, or by asking the retailer. All insecticides with the same number share the same or a similar mode of action, so James makes sure to pick ones with different numbers. The rotation of chemical insecticides is an important element of an integrated approach to combating resistance, along with non-chemical practices like pest monitoring, crop rotation, soil tillage, and the encouragement of predators. James is delighted. By rotating insecticides with different modes of action and by implementing integrated pest management practices, he has solved his insect problem in a sustainable way. This saves him money by increasing his yield and improving the quality of his produce. James also finds he does not need to apply insecticide as regularly and has more free time with his family. Farmers like James are not alone in the fight against insecticide resistance. In urban environments, mosquitoes can also develop resistance. This increases the spread of malaria and has a huge impact on public health. IRAC works everywhere to combat the development of resistance.
What is insecticide resistance? So, this is a heritable change in the sensitivity of the pest population. Ibig sabihin po ay ito ay namamana. So kung ang parents ay both resistant, posible na yung mga anak niya ay resistant din. So, and reflected in the repeated failure of the product to achieve the expected level of control when applied at its recommended rate. So, this means the product na you usually use ay nawawala na yung efficacy niya. Kasi ay ginamit mo siya sa buong crop cycle ng halaman. So this definition also the basis sa management ng insecticide resistance. So this figure is known as the selection process. That is one of the bases ng insecticide resistance. As we all know, insecticide resistance occurs due to the repeated use of pesticide that favors the increase of resistant individuals, or the red-colored pests shown in the figure. So the figure shows that before spraying, the first generation consists of 8 susceptible individuals, or individuals that can easily be killed by pesticide, and 1 resistant individual. Then after mag-spray, most susceptible individuals ay namatay na. Then on their next generation, there will be an increased number of resistant individuals. And if you use an insecticide with the same MOA, you will kill only the susceptible ones and favor the increase ng mga resistant na individuals. Ibig sabihin lang po ay applying lower or higher dose than the recommended rate ay pinapataas niyo po ang presensya ng mga insekto na mahirap mapatay ng insecticide. So, farmers' practice really has big impact sa IRM. So, another concept ng insecticide resistance ay fitness cause. So, this is the negative impact on an insect that is resistant to the insecticide. The insect loses or traded off qualities such as its ability to lay healthy eggs. So, may pangit din na epekto ang pagiging resistant ng insekto. So now, we go to management of insecticide resistance, or tactics that will delay the occurrence of insecticide resistance. So IRM refers to the deployment of strategy or combination of strategies, or so-called IPM, designed to delay the occurrence of resistance. So IRM is the combination of prevention strategies found in IPM. So this includes cultural control, monitoring, application of Biohand, and proper use of chemical control. So why do we need to prevent insecticide resistance? First is an increase in product life. We need to maintain the efficacy of those effective insecticides to give our farmers a wide selection of insecticide that can be used for rotation. Second, growers save money. Farmers prevent wasting money on those insecticides that cannot kill the insect, as well as prevent farmers to waste money by increasing the doses and rate of frequency of insecticide application. Also, this can encourage farmers to strictly follow the label and emphasize that even if you increase the doses or frequency, you cannot increase the mortality ng insect. And the third reason why we need to delay insecticide resistance is to have a more sustainable crop production. If the farmers use insecticide that is proven effective, then losses will be lessened and favor bounty harvest. The fourth one is protection of the environment. One of the recommendations to delay resistance is follow the label. If farmers strictly follow the label, then the harmful effect of pesticide residue against non-target organism will not be a problem. So now we go to general IRM recommendations. So there are 4 IRM recommendations, and we tackle them one by one. So una ay practice IPM. Under IPM, number 1 is prevention is the best strategy. So before planting, consider options for minimizing insecticide use. Incorporating different control mechanisms na yung pinakita ko sa IPM, like yung cultural, mechanical, and botanicals. So, insecticide application po ay must be the last option for controlling the pest. Number 2 ay selecting insecticides with care based on their label uses and in compliance with local extension advice, spectrum, effectiveness, and selectivity. Should not be harmful to beneficial. So, yung mga color bands po dun sa label ay hindi lang po yan design. So, we have to use po yung mga less toxic po na insecticide. And number 4 is understand the pests and monitor their population during the growing season. And number 5 ay practice yung clean culture. So we need to remove yung crop debris para ma-stop yung cycle ng pests. So yung second IRM recommendation ay follow the label. An insect population in the field consists of a mix of completely susceptible population, moderately resistant population, and completely resistant population. So when you apply a low dose or apply insecticide lower than the recommended rate, it will kill the moderately resistant insect and favors the increase ng mga completely resistant insect. At if you apply a higher dose than the recommended rate, it will kill the susceptible moderately and some of the homozygous resistant and retain yung mga completely resistant insect that favors the increase of resistant genes in the field. So not following the label lang po ay favors yung increase ng mga resistant insect na nagpapabilis po sa pag-occur ng insecticide resistance. So, ang third IRM recommendation is know the mode of action or MOA. So, I want to share a video made by IRAC that will help you understand kung ano ba yung MOA.
We explain the importance of using mode of action in insect resistance management. Bruno grows a range of vegetables on his farm using insecticides to control pests. However, this isn't a simple task. Recently, one of the products he'd successfully used for a long time stopped being effective. The insects are now flourishing and destroying his crops. So Bruno speaks to his local agriculture advisor, Anna. She explains that insecticides can work in different ways. They can have a different mode of action. Repeated use of the same insecticide leads to insects developing resistance against that mode of action, making them hard to control. As a solution, Anna recommends an alternative product with a different mode of action to control the pests. She strongly advises Bruno to vary the insecticides he uses in order to combat resistance. This sounds sensible to Bruno, but how does it work? Insecticides can be grouped by mode of action based on their site of action within an insect. Prevention or management of resistance is normally achieved by varying insecticide modes of action during the growing season. This is known as rotation or alternation. Bruno could also use multiple applications of the same mode of action over a defined period of time before switching to another. This is typically around a month and is called a window or block strategy. Application windows are normally calculated based on the time it takes for the pest insects to develop and reproduce. This is known as generation time. With this information, Bruno visits his local retailer to buy the new insecticides. But he's immediately faced with a challenge. How does he find out what mode of action a product has? Retailer Zach explains that in many cases, insecticide products clearly display the mode of action employed, represented by a code. He shows Bruno 4 different insecticides for controlling aphid pests, each with a different mode of action. To prevent resistance, products with different numbers should be used. For instance, Bruno could begin with number 23, then switch to 9B or 1A for the next application. Letters after a specific mode of action indicate chemical and structural differences between insecticides that have the same mode of action. These should only be used for resistance management if no other insecticides with different modes of action are available. Zach reminds Bruno to always follow the manufacturer's label recommendations. Importantly, Bruno also keeps in mind that insects are mobile, so it's crucial to avoid products for which resistance has been reported in nearby areas. Zach encourages Bruno to work with other local farmers, so they can share knowledge to help combat the threat of insect resistance together. In addition, Bruno discovers he can take other actions to control insects and reduce the cost of crop production. This is often referred to as Integrated Pest Management, or IPM. Using natural insect predators, removing old plants and rotating other crops that do not host the same insects are all ways to aid management. For more information on mode of action and resistance prevention, please visit irac-online.org.
Before you make insecticide selection or bago ka mag-spray, kailangan alamin mo muna kung ano ba yung MOA. So, insecticides found in the market have corresponding mode of action categorized by IRAC. IRAC is the Insecticide Resistance Action Committee, which is the international collaboration of chemical industries around the world. They are responsible for spreading technical documents on the proper monitoring of insecticide resistance. The chemical structure of the pesticide generally defines the target site and the mode of action of the target site. The target site is the physiological location ng nerves, muscle, respiratory, and midgut ng insekto, kung saan nag-a-act yung pesticide. Then the MOA or the mode of action is the action of a pesticide at its target site that causes the physiological disruption of the target site that eventually lead to death. So each pesticide has a group number to help growers make resistance management decisions. The recommendation ng IRAC to delay resistance is a window-based insecticide rotation based on MOA and not only by active ingredient nor brand name. So to help you identify what MOA or what insecticide belongs to, IRAC developed an app that is available in the Google Play Store. The feature of this app is that when you encode the active ingredient of the insecticide, it will determine what MOA it belongs to. In addition, you can access ng website ng IRAC, website ng herbicide, and for the fungicide. So, ito yung website ng IRAC. You can check their website to learn more about IRM. Also, from time to time, IRAC updating the list yung MOA classification scheme to include new developed insecticides. And yung below po ay proposed added label to all commercially available insecticides and will soon be visible to all insecticide in the market. So, yan po ay initiative ng mga private industry na ilagay dun sa mga registered approved pesticide sa FPA at saka yun po sa FPA. So, with this po, farmers will know what insecticide they can rotate. Also, you can check the FPA website to see the available insecticide that is surely safe for you at NPOs. Ang fourth IRM recommendation ay use of insecticide rotations by MOA. The determining factor that determines when to rotate is based on so-called window. The window can be crop per season, can be less than 50% of the crop cycle, or can be insect generation. They can be applied by a mixture or combined two MOA or rotation of single MOA. So yung mixture or combined two MOA, so hindi po farmers ang gagawa nun. So ano po yung mga insecticide company po yung gagawa nun. So yun. So hindi po ibig sabihin na mixture of two MOAs ay ano na po, pwede na po yung mga cocktailing. So yun po. So ayun. So, ito naman po ay yung mga scenarios of MOA rotations. So, yung sad phase po means poor control and happy phase means effective control. The first scenario is no alternation. Sad phase siya, so poor control. So, there will be highly selective pressure from the same MOA pesticide bombarded the area, thus no recovery ng susceptible population. Yung second scenario naman po ay rotation within a generation. So, sad phase, considered poor control. In this scenario, consecutive generation are exposed to the same MOA, but with different active ingredients. And the selection pressure doesn't change between generation, thus high risk to occur cross-resistance. So, cross-resistance po ay example ay is yung paggamit mo ng magkasunod na insecticide na may same active ingredient pero belong siya sa same MOA group. So example, yung flubendiamide and chlorantraniliprole. So pag sunod mo siyang ginamit, ayun, it induces cross-resistance kasi belong siya sa MOA group 28. So yung third scenario is rotation of MOA among pest generations. So happy phase siya, considered effective control. In this scenario, the consecutive generation will not be exposed to same MOA. Then the selection pressure doesn't increase within the generation. Thus will result in recovery of the susceptible population. At yung fourth scenario naman ay rotation within and between generation. Happy phase siya, considered effective control. So this is the ideal scenario. So under the fourth IRM recommendation is rotation by so-called windows or blocks. So the active window is defined as approximately the duration of one generation of target pest. And successive generation of the pest should not be treated with compounds from same MOA group. So another recommendation for IRM is to avoid exclusive use of one MOA throughout a crop cycle for a pest species with multiple generations. So, di ba po sa DBM, sa Brassicae, magkakaroon siya ng 6 generations. So, wag po tayong gagamit ng isang MOA lang. So, another recommendation for IRM MOA rotation is rotation of active and alternative windows or blocks. So, for example, a crop cycle is greater than 50 days and an insect generation of 30 days. So, the active window is the first generation of the insect that will be sprayed using insecticide with MOA group A. And the alternative window is the second generation of the insect that will be sprayed using insecticide with MOA group B. Then the spraying will be an alternation of MOA group A and B again. Then alternation will continue until the last day of approved spray before harvest. So, yun po. So, another recommendation for rotation of IRM MOA ay yung sa mga long season crop. Greater than 50 days. For this, it use treatment windows or use different MOA group per insect generation. For example, in Brassicae, yung pest niya ay DBM or the diamond back moth. In one whole crop cycle of Brassicae, DBM will have 6 generations. Thus, you need to use 6 types of insecticide with 6 different MOAs. So, another recommendation for rotation of IRM ay sa mga short cycle crops, yung less than 30 to 50 days. For this, we use the crop cycle as treatment window. So, for the entire crop cycle, we will use one insecticide with one MOA. Then to the second planting of different crop with short life cycle, another insecticide with different MOA. So, for this part, I will share to you the generated outputs from ongoing project related to IRM in FAO. So yung part 1, I will share to you yung IR monitoring framework. Part 2 ay yung baseline data, yung mga practices ng local corn growers sa Quezon and Isabela, at yung baseline susceptibility ng FAO mismo. At yung part 3 ay yung recommended insecticide for corn growers that they can rotate for the entire corn cycle. So, ito po yung proposed na insecticide resistance monitoring framework namin. So, it consists of 2 parts, the research and development part and the technology transfer part. The first part will be implemented with collaboration by NCPC, FPA, and BOX. This part focuses on data gathering of the baseline data such as farmers' adoption and the recommended IRM, potency data of FAO in corn, IRM molecular profile of FAO, on selected insecticides, and also field validation of insecticide to screen insecticide that will give an acceptable efficacy against FAO. That will be used to craft a window-based program that will use alternation, rotation, combination, mixture application with frequency and timing of application. Then the results will be integrated into an interactive application, so-called spray. Yun po yung submitted proposal namin sa DA bar. Then, also yung policy, drafted policy na ito-transfer po natin sa DA, FPA, and BAPS para yun po yung i-endorse nila. Then, after the policy signed by DA, FPA, and BAPS, we will transfer it to insecticide retailers and farmers for their access. We propose spray in DA bars is one of the roots of pesticide misuse is techno-transfer difficulty. So we all know na yung mga generated outputs ng research ay available lang through IEC and also web. But due to restrictions ng travel, lack of financial aid, unstable provision of high-speed internet connection, ay malaking problema po dito sa atin. Kaya we must utilize yung smart agriculture to speed up techno transfer. Kaya po pinapost namin po yung spray. Yung spray po is an Android and iOS application for IRM that doesn't require stable internet connection and offer a text message alert to those with no smartphones. So this app offers 3 features, yung spray calendar, spray maps, and spray learn. So, ito naman po. So, for transboundary pests such as armyworms, farmers are the pest affected group. Thus, we must equip them with the right control method to prevent problems such as pesticide misuse. Thus, to be able to craft proper control methods, baseline survey must be done. Information such as crop protection practices, farmers' knowledge of the pest, this will guide us on practices that lead to misuse. And with this, we will make recommendations to correct the misuse practices. So now, I will share with you the conducted baseline survey from corn growers in Isabela and Quezon. So based on this data, governments such as DA is one of the major sources ng technical training ng local corn growers. This data show that DA has a big influence on crop protection practices of farmers. Thus, academe and DA agencies must collaborate and be proactive to solve the problems sa pesticide misuse. So, according to our farmers, fall armyworm is the top pest encountered and FAO is present throughout the crop stages of corn. But the highest infestation was observed at 1 to 2 weeks old plant. FAO is present from after planting at hanggang sa harvest. So, ito po yung similar dun sa previous slide. So, this data shows you the knowledge of corn growers about the pest. So, most farmers know that the life cycle of FAO is long, probably since FAO is observed after the corn is planted until harvest. And few know that FAO has a short life cycle of about a month and it will have 4 generations until harvest. So, for the knowledge about the destructive stage of FAO, most farmers are correct. For feeding behavior, only a few farmers know that FAO can damage not only the leaves but also the ears, which will have a big impact dun sa market sales nila. So for transboundary pests such as armyworms, insecticide remains the #1 control measure among farmers. But the observed problem with this is insecticide resistance resulting from the misuse of pesticide. So this slide is the recorded farmers' practice in major corn growing areas. Farmers showed an increase in usage yung sa mga non-insecticidal material agents sa FAO between 2016 up to the present. So farmers resort to non-insecticidal materials like yung detergents, gasoline. At also sa harabas ng onion, they use holy water before para lang makontrol yung pest. So to control the pest, at saka gumagamit din sila ng mga high health risk insecticides like yung banned, restricted, and smuggled insecticides. So this practice showed the desperation of farmers as well as inadequate proper know-how on how to control yung mga harabas. So for farmers, the selection of insecticide based on MOA. So there is a decrease in usage across different MOAs before FAO and during FAO, except for Group 4A neonicotinoids, 22A oxidizins, and Group 28 diamides. The biggest increase observed such as diamides were probably due to the release program ng DA noong 2019, kung kailan na doon na-confirm ang presence ng FAO. So, nung lumabas yung FAO, nag-release ang DA ng recommendations ng yung magagamit ng insecticide ng mga farmers. So, yan. So, most farmers do not know the importance of follow the label. They practice cocktailing and mix 2 or more insecticide. They mix weak insecticide with strong insecticide and categorize the efficacy of insecticide based on the price. Most farmers believe that when they mix insecticide, the efficacy against the pest increased, but they did not know that the risk in health and environment was also increased, and it speeds up insecticide resistance. So most farmers do not conduct pest monitoring before insecticide application. So now we go to baseline susceptibility studies of PAO against selected insecticide. So this data will answer the question, is the approved recommended rate enough to kill the Philippine PAO populations? So the data generated was presented as a poster at the virtual conference at the 52nd PMCP Anniversary and Scientific Convention last July 2021. So pwede nyo rin po itong i-access sa website ng NCPC. So based on the conducted baseline susceptibility assay using lick-dip method and analyzed using probit analysis program, the insecticides that are found resistant based on the effective dose is the recommended rate ratio or index of carb, lambda-cyhalothrin, carbosulfan, and Bacillus thuringiensis aizawi. Using the generated response curve, the insecticides were categorized as slow and fast-acting. Based on the response curve, fast-acting insecticide or those insecticides where high mortality occurred after 24 hours, such as lambda-cyhalothrin and carbosulfan. And yung slow-acting observed when high mortality occurred 48 hours after treatment, such as indoxacarb and BT. And those values in red fonts mean the effective dose is higher than the recommended rate and confers the presence of insecticide resistance. So this slide shows the insecticide that have no insecticide resistance, such as chlorfluazuron, tetraniliprole, indoxacarb A, and cyanteraniliprole, and all of them are categorized as low-acting insecticides. So additional insecticides that have found no resistance, such as mixed insecticide, yung chlorantraniliprole and thiamethoxam, spinosad, pyridalil, emamectin benzoate, and spinetoram. Using baseline susceptibility assay, you can compare the susceptibility response, yung mga different local FAO population per insecticide, and will guide you on where in the Philippines where pesticide misuse is rampant and needs attention to correct the misuse. For example, in carbosulfan, Pampanga FAO population have an observed EDR ratio at LD50 na 20.10. Yung Quezon naman na FAO population ay 7.7. And Cagayan has 3.49. So it means that the effective dose in Pampanga needs to increase 20 times than the recommended rate to kill 50% PAO population, while Quezon requires only 7.7 times higher than RR, and Cagayan needs 3.49 higher than RR. This means pesticide misuse of carbosulfan is highest in Pampanga, followed by Quezon, then in Cagayan. So itong slide naman po ay additional insecticide that were tested to determine yung different PAO population responses sa cyanteraniliprole, spinosad, and pyridalil. So now we go to field validation. So after mong gawin yung baseline susceptibility studies, you must validate the results under field condition. So for field validation, insecticide given special use permit listed at FDA and MAPS were assessed the efficacy under field condition to give farmers choices on insecticide that can be used for rotation. So these are the insecticide used for field validation. We have conducted several trials to categorize selected insecticide from no efficacy to highest efficacy or from fair to excellent insecticide, using pest count, damage, and yield assessment. We also conducted trial to determine the right timing and frequency of application. Also included treatments to determine different varietal response performance. So these trials were headed by scientist Maria Vina Basero. So this is the result of damage rating using Davis rating scale from the field efficacy trial conducted from September to December 2020. As shown in the figure, the rating per insecticide was labeled from 1 to 6, with 1 being the highest efficacy and 6 means no efficacy. So ito naman po yung result ng second trial. The figure showed the results of mean damage assessment using the Davis rating scale from 9 sampling dates assessing conventional insecticide against FAO conducted from January to April 2021. In this figure, you will see that it was arranged in ascending order and grouped into 1 to 4 based on their efficacy against FAO and groupings of t-tests using LSD with 0.05 level of significance. 1 means highly efficacious, 2 means efficacious, 3 moderate, and 4 no efficacy or similar with the performance nung untreated natin. So for botanical insecticide, this is the result of field efficacy. Part 2 siya ng second field trial. Matrin was considered highly efficacious against FAO, while potassium salt and fatty acid were labeled efficacious. But meron pong negative impact yung potassium salt and fatty acids kasi it produced shortened internodes and produced small ears. This insecticide, so yung mga botanical insecticide po ay available po yan sa market. So you can check po yung website po ng BAPS as reference po. So based on the several field efficacy trials conducted, these are the recommended insecticide for rotation specific for FAO that will help delay the occurrence of insecticide resistance. In the table, you will see the active ingredients and MOA group. They are grouped from excellent, group 1, good, group 2, and fair, group 3. The recommendation is that you may use any of those insecticides classified as excellent under group 1. If a follow-up application is needed, use another insecticide belonging to a different mode of action from the one used in the first application. Those belonging to groups 2 and 3 may also be used if the population of FAO is not very high. The window that can be used ay 2 weeks. So the duration of MOA A is 2 weeks, then followed by MOA B. Then can use MOA A after a month. AI with U and MOA can be counted as another MOA. Avoid mixing or cocktailing of different MOAs. Apply insecticide when needed means monitoring first before spraying. So yung right timing ng frequency and application ay ongoing pa po. So yun po, matatapos na rin po. So yun po yung idadagdag po namin. So to speed up techno transfer, we propose a project called Spray, an Android and iOS application for IRM that doesn't require a stable internet connection and offer a text message alert to those with no smartphones. So this Spray app has 3 main features. Yung Spray Calendar. So this feature will offer a recommendation based on a window rotation of MOAs of insecticide. In addition, we will provide text notification like the NDRRMC alert for those farmers with no Android and smartphones. So yung second feature ay yung Spray Map. This includes information on effective insecticide recommendation based on MOA, insecticide history, area-specific availability of insecticides, kasi po yung, for example, yung plant shield. So, nahirapan po kaming bumili noon kasi sa Davao lang po siya mabibili. At wala po sa Luzon kaming mahanap na supplier. Also, yung farming habits po ng ating farmers ay kasama rin po dito. Third feature ng Spray Learn ay show information on the proper use of insecticides. Tapos, meron din po tayong insect libraries that show the biology, life history, behavior ng pest, alternate host, images ng pest and alternate host, and season of emergence. Also, may Spray Learn din. We'll show a listing of IRAC MOA and its corresponding active ingredients, mapped to 8 FPA-approved insecticides. So, ito po yung aking references. So, before I end this presentation, I would like to acknowledge DA and DOSTP card for funding the project, ang project staff po at City Agriculturist sa Quezon at Isabela. So, maraming salamat po.
Maraming salamat po, Ma'am Karen, for discussing itong insecticide resistance management. Salamat, Ma'am. Time check. It's already 11:42 a.m. So, may isa pa po tayong speaker. Hindi na po natin patatagalin pa. Actually, i-share po niya ang kanyang mga experiences with Grow Asia's ASEAN FAO Action Plan. Isa po siyang entomologist at university researcher dito sa NCPC. Siya po ang ating guwapong-guwapo, si Mr. Randolph Candano. Sir Randy?
Thank you, Joy. Good morning sa lahat na nanonood via Zoom, gayon din sa YouTube at Facebook Live. This morning, I will be sharing my experience as a project associate in one of Grow Asia's efforts in facilitating multi-stakeholder partnerships for sustainable agriculture development. I will share my presentation following this outline. I will first discuss what is Grow Asia and what are they doing, and then what is this ASEAN FAO action plan, and lastly, my experiences as a project associate of Grow Asia. Now, Grow Asia is a multi-stakeholder platform that builds field, national, and regional level partnerships to broker market-driven solutions that cultivate inclusive, resilient, and sustainable food systems in the ASEAN region. Grow Asia was established in 2015 by the World Economic Forum in collaboration with the Association of Southeast Asian Nations, or ASEAN, to convene, facilitate, and help scale action-focused partnerships. In 2020, Grow Asia was accredited as an entity associated with ASEAN due to the important role of Grow Asia placed in the region, particularly in facilitating multi-stakeholder partnerships for sustainable agriculture development. Grow Asia do this by facilitating collaboration between key players from the region's public, private, civil society, and farmer organizations around macro-level issues and the development of inclusive and sustainable agriculture value chains. Grow Asia comprises the Regional Grow Asia Secretariat in Singapore, 6 country partnerships, each supported by an in-country team, and 44 working groups organized around specific cross-cutting issues or value chains. Globally, countries who have been able to create platforms where the public, private, and civil society sectors convene and plan together tend to have a stronger agriculture sector. As such, Grow Asia has catalyzed and supports 6 country partnerships in Southeast Asia as national public-private partnership platforms for sustainable agriculture. And these are Cambodia through Cambodia Partnership for Sustainable Agriculture, Indonesia through Partnership for Indonesia Sustainable Agriculture, Myanmar through the Myanmar Agriculture Network, Papua New Guinea through Grow PNG, and Philippines through the Philippines Partnership for Sustainable Agriculture, and lastly, Vietnam through Partnership for Sustainable Agriculture in Vietnam. The Grow Asia Network involves more than 580 organizations across the region, representing the public sector, multinational corporations, local agribusinesses, civil society, farmer associations, and research and academia. At the regional level, the Grow Asia Secretariat in Singapore provides strategic support to the country partnerships and coordinates activities around work streams with the potential to increase the scale of their network's impact. These work streams are currently built around a regional response to COVID-19, supporting the digital agri-tech ecosystem, promoting gender mainstreaming in agriculture, supporting regional response to pests and diseases, promoting responsible agricultural investment, and critically supporting regional knowledge exchange. Grow Asia have 6 major regional programs in a partnership with the ASEAN Secretariat. One of the programs is designed to help the poor and vulnerable during this pandemic. Grow Asia's conversations with agriculture leaders in Southeast Asia have revealed that they believe digital technologies such as tools for enabling access to financing, digital marketplaces, or traceability solutions are set to positively transform the way smallholders interact with agribusiness value chains. Women make up more than 30% of the agricultural labor force in Southeast Asia, and therefore, food and agriculture value chain actors must understand the specific needs and challenges women face. That is why Grow Asia contributes to women empowerment. Grow Asia also builds partnerships with policymakers, agribusinesses, financial institutions, farmer organizations, multinationals, and NGOs to drive regional adoption and application of responsible agricultural investment in the ASEAN. Also, Grow Asia has a strong commitment to learning and knowledge sharing. Lastly, as a dynamic and nimble organization with strong ties to the ASEAN Secretariat, the ASEAN member states, numerous multi- and bilateral agencies, and the key players in the region's agriculture sector, Grow Asia is uniquely positioned to facilitate regional responses to outbreaks of pests and diseases, particularly fall armyworm or FAO. And this is where my work as a project associate evolves. In 2019, ASEAN supported the development of a regionally coordinated response and requested that Grow Asia with the ASEAN Secretariat and the Vietnamese government develop a regional FAO strategy. The ASEAN Action Plan on Fall Armyworm Control was subsequently approved as a regional action plan in August 2020. This comprehensive plan sets out the goals, objectives, and work programs to manage the pests over the next 5 years. And on October 21, 2020, ASEAN Ministers of Agriculture and Forestry agreed to a comprehensive regional action plan on fall armyworm. This destructive pest, which arrived in 2018, is now established across Southeast Asia. The action plan sets out the goals, objectives, and work programs to support countries to respond to, monitor, and manage FAO across Southeast Asia. The ASEAN FAO Action Plan focused on 6 work programs, namely coordination, communications, and management, knowledge and policy, farmer learning and support, dynamic pest crop livelihood baseline, surveillance and impact, and IPM toolbox. The ASEAN FAO Action Plan has a range of activities that fall under each work program. These projects focus on a key area of work under the action plan. The first flagship project is the Regional Resistance Management Plan, which is focused on making sure that we maintain all options in the IPM toolbox for farmers to use in controlling FAO. It involves work on research, coordinated policy approaches, FAO management guidance, and the development of host plant resistance. The second project is Regional Surveillance and Monitoring Platform. Since FAO is a transboundary pest that respects no borders, it also moves quickly and across large distances. Understanding where FAO is in the region, how and when it migrates, and how bad infestation levels are is vital to informing management decisions on how best to manage and control FAO. The third program is biocontrol, which aims to understand the opportunities of using to manage FAO as well as identify and address barriers to its use. The project also aims to build a network of practitioners and research institutions across the region to help promote effective and economical biocontrol approaches for FAO control. The fourth project is farmer communication and action. Farmers need the ability to make informed decisions based on a choice of options and tools which are accessible, affordable, safe, and effective at controlling fall armyworm. The fifth project, which is drones and digital IPM, offer huge potential to help manage plant health and FAO as part of an integrated pest management approach. Again, Grow Asia contributes to women empowerment, hence the sixth project, which is Women as IPM Leaders, focus on women as critical leaders in IPM. Now I will be sharing how I get the chance to be one of the project associate for the ASEAN FAO Action Plan. Grow Asia is seeking in-country consultants to work with stakeholders in transforming agriculture and food systems in Southeast Asia. They are looking for experts or somebody who have experience in agriculture, inclusive business models, international development, value chains, or have expertise in finance, gender, or environmental issues. So if someone is interested, they need to fill in the consultants form available in Grow Asia website to be able to join their general pool of consultants or experts, and they will be in touch as opportunities develop. In my case, I was asked by my colleagues, our scientists at the National Crop Protection Center, if I am interested to apply because someone from the ASEAN FAO Action Plan is looking for interns. And then I submitted my CV directly to the project lead, which is a representative of Grow Asia in the name of Dr. Alison Watson. In the ASEAN FAO Action Plan website, you will also see this in the forum. This is a post from Dr. Alison Watson looking for interns who will help her in achieving the objective of the ASEAN FAO Action Plan. So I started my stint in the ASEAN FAO Action Plan in June 2021, and here are the members of the team. We have Dr. Alison Watson as the project lead. She is from New Zealand but is based in Singapore, where the office of Grow Asia is located. We directly report to her as project associates. And we have Ratna Rubiana, my co-project associate from Indonesia. She is a PhD student and currently working on FAO resistance. We also have Ignatius Putra Andika, also from Indonesia. He is now working at the Department of Biology, University of Atma Yagya Yogyakarta, and a project that he have worked on related to integrated pest management and FAO is the assessment of farmers' perception of insect pests on maize or corn. We have Samuel Urn from Cambodia, who is also seeking a PhD degree and currently working on mass rearing and biological control of fall armyworm. And of course, myself, Randolph from the National Crop Protection Center, College of Agriculture and Food Science, UP Los Baños. Now, we are selected by Grow Asia based on our skills and expertise, which is related to plant pests and disease management. And our role is project associate for the ASEAN FAO Action Plan for 6 months already and counting. As a project associate, our task is to collaborate closely with the head of the Secretariat and project associates of the ASEAN FAO Action Plan at Grow Asia, as well as other relevant Grow Asia staff and project contractors to deliver the following activities in the Philippines. First, we act as an expert contributor to the FAO Knowledge and Innovation Hub, answer technical questions, and respond to comments posted in the forums. Second, we conduct interviews with farmers and experts using an agreed protocol who have experience of FAO incursions on their farms and produce in English a summary of those interviews for posting on the Fall Armyworm Knowledge and Innovation Hub. Third, we need to identify all research teams and organizations in the Philippines that are working on integrated pest management, fall armyworm, biological control, pesticide resistance, and research, providing a summary of the research focus and key contacts. The fourth is we need to identify the key government contacts and agencies that work on, develop policy for, and implement regulations related to integrated pest management, fall armyworm, biological control, pesticide resistance related to maize crops. The fifth is to identify regulations, approve pesticides and technologies relevant for fall armyworm control in the Philippines, and provide a written list of this. Moreover, we are also tasked to carry out data collection and information gathering to support the development of information resources for the Fall Armyworm Knowledge and Innovation Hub as requested. And lastly, we assist in the development and management of webinars and workshops held by the ASEAN FAO Action Plan. As an expert contributor, I have answered questions and comments posted in the Fall Armyworm Knowledge and Innovation Hub. I also posted some information related to Fall Armyworm management, specifically biocontrol. And here you can see one of my previous postings, which is the use of earwigs as a potential biocon agent against fall armyworm. This is currently being practiced. This is currently being studied in the Philippines. I also managed to interview several corn and rice farmers in Pampanga who are affected greatly by fall armyworm. I made a video recording, translate the local language into English language, and posted it on Grow Asia YouTube channel and on the Fall Armyworm Knowledge and Innovation Hub. Aside from farmer interviews, I also interviewed some experts working on fall armyworm monitoring and management. I interviewed 2 experts from the National Crop Protection Center who happened to be our speakers also for this seminar, Mr. Gideon Aris Borgoño and Ms. Melissa Montecalvo. My interviews with them are posted as blog and are available on the Fall Armyworm Knowledge and Innovation Hub. Now, part of my task is to identify different research teams and institutions working on fall armyworm. And here in the Philippines, all fundings on fall armyworm projects and researches came from the Department of Agriculture through the Bureau of Agricultural Research, or the ABAR, Bureau of Land Industry, and the different DA regional field offices. And from the Department of Science and Technology through one of its sectoral council, which is PICARD, or the Philippine Council for Agriculture, Aquatic, and Natural Resources Research and Development. Now, from the national government through the Department of Agriculture, Bureau of Agricultural Research, and PICARD, funds were allocated for research and development on fall armyworm, and UP Los Baños is the recipient of this funding. There are only 2 institutions from UP Los Baños that leads the research in fall armyworm: the National Crop Protection Center and the Institute of Weed Science, Entomology, and Plant Pathology. As of now, there are 8 projects being conducted related to fall armyworm in UP Los Baños, and another 1 project being led by the Bureau of Land Industry. I just want to walk you through the different projects being undertaken for the management of fall armyworm. We have project being led by the Bureau of Land Industry. This is the development of early warning system and database management of corn arthropod pests and diseases in the Philippines. We also have project from the National Crop Protection Center being led by Melvin Ebuenga and Mr. Gideon Aris Borgoño, which is the remote monitoring of transboundary plant pests and the development of an early warning system against fall armyworm. through phenology and distribution modeling. We also have projects being led by Dr. Jessamine Adorada from the Institute of Weed Science, Entomology, and Plant Pathology in collaboration with the National Crop Protection Center, and the title of their project is the Identification and Preliminary Evaluation of Natural Enemies Against Fall Armyworm. We also have a project from NCPC being led by scientist Marcela Nabacero, which is the biological control of fall armyworm using entomopathogens. We also have a project being led by Ms. Melissa Montecalvo. This project is already finished. This project is the verification and technology transfer of management strategies against fall armyworm of corn, mango, sausage fly, onion armyworm, and fusarium wilt of banana. Another project from the National Crop Protection Center being led by scientist Marcela Nabacero is the characterization, mass production, formulation, and utilization of metarhizium relay for increased potency against fall armyworm, and the biological control-based pest management of fall armyworm using NPD, earwig, and entomopathogenic fungi and diatomaceous earth. Another project being led by Ms. Karen Ardes and Mr. Gideon Arns Borgonio of NCPC is the insecticide management and susceptibility studies on fall armyworm and the development of pheromone traps for the monitoring of the fall armyworm. Aside from the organizations and institutions working on FAO, I am also tasked to identify different organizations and institutions working on IPM and identify key contacts in their research interests. So here are some of the organizations working on IPM. So this is a work in progress because there are many organizations and institutions who are working on IPM. So of course, we have the Bureau of Plant Industry through its Crop Pest Management Division, the National Crop Protection Center, and the Institute of Weed Science, Entomology, and Plant Pathology, and the Institute of Plant Breeding. They are all from UP Los Baños. We also have the Department of Research Office of CLSU, Biological Control Research Unit of the De La Salle State University. We also have the Department of Entomology in the University of Southern Mindanao, the College of Agriculture in Cagayan State University, the Department of Pest Management, College of Agriculture from Visayas State University, the Mariano Marcos State University, and the Philippine Rice Research Institute, or PhilRice. And we also have the different regional field offices through their respective regional crop protection centers of the Department of Agriculture. We have a total of 13 regions plus 2 autonomous regions. And of course, aside from government institutions, state universities and colleges, private universities, there are also industry partners who are constantly collaborating with different research institutions for the control and management of fall armyworm. In the Philippines, from the private sector, there are 2 umbrella organizations that are actively involved in pest management. These are CropLife Philippines Inc. and Crop Protection Association of the Philippines. These organizations consist of member companies who are into the distribution and use of pesticides. Moreover, I am also tasked to assist in webinars and workshops online, and so far we have conducted several workshops already, and we have 2 more workshops in the line, one on December 7th and the other one on December 9th. These workshops will cover topics on women as IPM leaders and drones and digital IPM. Now, with this, I would like to leave you with some takeaways. And these are, first, Grow Asia's way of working is anchored upon SDG 17, or Sustainable Development Goal 17, where sustainable development is achieved through global and multi-stakeholder partnerships. Second, my experience in Grow Asia opens a lot of opportunities for collaborations among ASEAN countries and a chance to level up our profile. And lastly, through Grow Asia and ASEAN FAO Action Plan, I was able to meet and connect with some global experts on IPM. So that's all. Thank you very much for listening and watching. And for more information about Grow Asia and ASEAN FAO Action Plan, just visit the Grow Asia website and the ASEAN FAO Action Plan website that you are seeing on your screen. Again, thank you very much.
Okay, maraming salamat po, Sir Randy. Ayan, so tapos na po natin ang ating 7 speakers. Medyo may extend po tayo ngayon, ano po, kasi meron pa po tayong open forum. So para i-assist po tayo sa ating open forum, tinatawagan po natin ang isa nating kasamahan dito sa webinar series team, si Ms. Romaline Limpiada, to facilitate ng ating pong open forum. Ms. Roma.
Hello, Ms. Joy. Marami pong salamat. Ayan, so hindi na po natin patatagalin ang ating po. Rinig niyo po ba ako?
Yes, loud and clear.
Natin patatagalin ang ating pong sisimulan na po natin ating open forum at panigurado ready na po ang ating po mga resource speakers. Tatawagin po natin muli sila si Ma'am Sally, Sir Gids, Ma'am Aisa, Ma'am Bambi, Ma'am Karen, Ma'am Marie, and Sir Randy para po sagutin ang mga katanungan ng ating po mga participants. So sa mga gusto pa pong humabol na magtanong, may mga questions pa po, pwede nyo pong ilagay sa Zoom chat box kung kayo po ay nasa Zoom, or pwede nyo pong i-click yung raise hand button nyo kung nasa Zoom po kayo para po makapagbigay po kayo ng live question. Kung nandun naman po kayo sa YouTube or Facebook, ay doon naman po kayo sa comment section nila maglagay. So hello ma'am. Okay, so para po sa una nating una ko pong nakita si Sir Gids. Ayan. Ayan, Sir Gids. So, marami po dito interesado na makipag-collaborate po sa inyo. Posible daw po ba na makipag-collaborate sa inyo regarding po sa RPAS and future modeling of FAO population dynamics? So, ito po ay si Sir Bernard Panabang and Jacob Malagi.
Ay, okay pa. Oo naman po, sure po. So we're looking for collaborators po talaga from private and public stakeholders po, no. So especially kasi dun sa tawag dito sa validation po ng ating mga models and sa pag-conduct po ng tawag dito ng monitoring po. So welcome po ang ano. So meron din po tayong mga pinropose na rin na project po, yung continuation po ng retrap. Remap naman po, remap. So hindi lang to nakafocus na sa transboundary pest, hindi lang sa transboundary pest, kundi sa mga major pests na rin ng ilang major crops. So hopefully approve po ito for funding next year. Yan po. So yan. Thank you.
Sir Gibbs, pahabol po, saan daw po or paano daw po mag-avail ng retrap manual?
Ayun po. So yung retrap manual po, yung retrap manual 1 for fall armyworm, currently parang binibigay namin siya for those na kumbaga parang may kakaibat na training dapat sana yon. So kung may training, so doon lang po tayo makakakuha ng manual. So kasi medyo komplikado kasi yung manual, kaya kailangan talaga ng hands-on training. So yung ginawa natin sa Nueva Ecija, kinaya siya ng 2 days. So hands-on and theoretical. Both sa pag-processing ng images, sa analysis, and yung pagpapalipad ng drone. So mga 2 to 3 days training po 'yun. Thank you po.
Marami pong mga tanong sa inyo, pero unahin po muna natin ang question po for Ma'am Sally. Hi Ma'am Sally, pa-on po ng camera at ng microphone po. So ito po ay question din po mula sa Zoom kay Sir Bernard, from Sir Bernard Panabang. Sabi po niya, it is observed that pest counts of Asian corn borer is almost zero in the field where FAO is present. Posible po kaya na ito ay dahil sa cannibalism by FAO? Since earlier po na-mention niyo po sa presentation niyo yung cannibalism ng FAO. So is the absent, what are your thoughts po regarding the pest population dynamics of Asian corn borer and fall armyworm? And yung last question po niya is, will FAO replace the ACB as the most destructive insect pest of corn in the Philippines?
Sa kasalukuyan, sa mga field trials namin, wala na kaming namomonitor na corn borer. So, malamang FAO na ang mangunguna niyan.
Kung cannibalism ba?
Dahil po kaya sa cannibalism, kaya po kaya nawala?
Ang nauuna kasi ang FAO infestation. So, sa insects naman, pag nauna na ang isa, hindi na nagtutuloy yung iba, no? At saka based on crop history, ang corn borer naman late talaga siyang nag-i-infest. Pag nauna na yung FAO, hindi na ito, yung corn hindi na palatable malamang sa corn borer. So, hindi mo lahat ma-attribute sa cannibalism, ano?
Thank you po, Ma'am Sally, sa clarification. And next question po natin for Ma'am Melissa. Sabi po ni DM Choco Hills from Zoom, maaapektuhan po ba ng AMAG or yung mga EPF if ever na mag-apply ng mga fungicides for other fungal diseases?
Maraming salamat po sa inyong katanungan at tama nga po kayo na magiging effective lang yung integration nitong entomopathogenic fungus kung siya ay magiging compatible sa mga agrochemicals. Present po ay chinek namin yung mga literatures abroad and merong mga varying effect. That's why kailangan po natin ng local data dito sa Philippines para malaman po natin kung sila ba ay toxic or sila ba ay compatible sa ating mga entomopathogenic fungus. At yan po yung aming gagawin dito po sa laboratory. At ang importante lang po dito ay gumamit po tayo ng maging judicious po ang ating paggamit sa mga pesticides.
Marami pong salamat, Miss Mel. Yan po. Next question po natin ay para po kay Ma'am Bambi. Ma'am Bambi, paano daw po nire-reproduce ang EPN and paano po kaya siya ina-apply po sa field?
Hello. So, currently we're reproducing EPN in vivo. So sa insekto, that's why we're looking for yung mas appropriate na host para mas marami ang IJs namin. But you could also reproduce them in vitro using liquid medium or solid medium. So doon sa unang naging project namin, we were able to reproduce using solid medium. Then application sa field is pwede siyang i-spray. So yung may mga formulations kasi na sprayable siya.
Ma'am
Thanks, Roma.
Ma'am Karen or Ma'am Marie, from Sir Edrian Emmanuel Gladstone na nasa Facebook, what is the effect of insecticide rotation or use of insecticide with different modes of action sa mga beneficial insects po natin? Meron po bang effect, Ms. Karen?
Yung epekto ng insecticide rotation sa insekto, so actually ang nakaka-epekto lang naman sa mga natural enemies ay kapag hindi ka nag-follow ng label. So yun. So, pero meron din recorded na sa mga natural enemies na kapag hindi ka nagro-rotate ng insecticide, tumataas din yung resistance nila dun sa insecticide din. So, ganun.
Mag-add lang ako dun, no? So, yung sa akin kasi evaluation kami ng biocon agents, so hindi kami nag-assay ng anong effect talaga ng insecticides sa biocon. So, pero dun sa tanong niyan na kung may effect, I think yung recommendation kasi ng biocon, usually hindi siya kasabay ng insecticides. Meron pa rin yan interval para less yung exposure ng insecticide ay ng biocon agent sa insecticide. And usually, mababa yung population, mas maganda na mababa population ng peste kapag nandun na yung i-release na yung biocon para mas effective siya.
Hi, Roma. Pwede rin
Yes po.
mag-add?
Oh, yeah, sure po.
Mag-add din ako dun sa question ni Sir. No? Usually, ang effect ng mga insecticide dun sa mga beneficial insects ay indirect. Kasi since namamatay yung target pests ng insecticides, nababawasan din yung parang natural prey ng mga beneficial insects. So yung epekto ay indirect. Parang ganun. Thank you.
Roma, for EPN naman, so may mga chemistries na compatible with EPN, just like with EPF. So kailangan alam mo kung anong active ingredient ang pwede mong isabay with EPN.
Na kailangan i-consider, hindi lang siya isa. Okay. So, next question po, Ma'am Selly. Ano po yung common na harabas na umaatake po sa sugarcane? And what are the common damages po nito? Hello, Ma'am Selly. Naka-off po yata ang microphone niyo po. Yes, Ma'am Selly. Ano po yung common po na harabas or armyworm po sa sugarcane?
Ang bagong reported na harabas ng sugarcane ay ito ngang fall armyworm, pero may mga borers na yung dati pa sa sugarcane, pinakabago itong harabas na topic natin ngayon, fall armyworm.
Hindi po tayo ang makakasagot nito, pero baka po meron po sa inyo na sabi po ni Sir Jesse na nasa Zoom, kailan po kaya magiging available ang spray app sa Google Play Store? Miss Karen.
Yung spray app ay proposal pa lang siya na sinubmit sa DA-BAR. Na-review na siya, so pag nabigyan na kami ng signal na mag-implement next year, so kung mag-start kami ng January, probably mga mid ng 2022 ay maging available na siya sa Google Play Store.
From Sir Renato Avenue po, sabi po niya, posible po ba na mag-atake sa rice field ang FAO kahit magkaiba sila ng cultural management ng corn? Sino pong gusto sumagot?
Ang FAO ay napareport din sa rice, sa Region 2, pero kaya siya lumipat sa rice kasi nawalan ng corn, walang nagtanim ng corn after corn. So, ang standing crop na lang at that time ay mga punla ng rice. So, yung mga nag-pupate na nag-emerge, so wala silang pupuntahang ibang corn. So, sa rice lumipat.
Lipat sila sa iba nilang pwedeng kainan. Yan. Isa pa pong question. No-consider po ba ang environment if nag-a-apply po ng EPN sa field? Kasi more on desiccation. Kasi based sa experience po ni Sir Cyril Tura ng DORS.
So, Roma, akin ba yun?
Yes, Ma'am Bambi.
So, critical yung timing of application. So, and there are also studies na pwede ka mag-select ng EPN, no? So kasi yung EPN na population namin ngayon hindi pa yan talaga pure na meaning na isang clone lang siya, meaning yung kanyang genetic makeup is really isa lang, no? So mixture pa yan. So what you can do is you can select for the desiccant tolerant, no? Doon sa isang pinanggalingan ko na lab, nag-hybrid sila ng different populations ng EPN of the same species, and they would like to select yung desiccation resistant, temperature resistant, at saka yung maraming progenies. So as of the moment, ang pwedeng gawin ngayon is yung timing ng application. So better apply paggabi.
Thank you po, Ma'am Bambi. For Ms. Karen po, ang pag-combine daw po ba ng dalawang different mode of actions ay nakakapagpataas ng efficacy?
Ano po, so yun po ay cocktailing. So ano po yun, hindi po natin nire-recommenda yun. Tsaka hindi po niya napapataas yung efficacy kapag pinag-combine mo yung dalawang insecticide na binili mo sa market. So hindi po natin ini-encourage na gawin po yun ng mga farmers kasi pinapataas lang nila yung risk ng yung sa health at saka yung sa environment.
So I think marami pa pong question pero tayo po ay kulang na po sa oras. So sasagutin na lang po sa inbox na atin pong mga resource speakers ang inyo pong mga katanungan. So muli marami pong salamat sa ating pong mga resource speakers for accommodating our participants' questions, and salamat po sa mga participants for their active participation. Sige po, sasagutin na lang po nila sa chat box. Again, back to you, Ms. Joy.
Salamat, Ms. Roma. So at this point, muli nating tawagin ang ating mga speakers to award ang kanilang certificate as a resource speaker ngayong umaga. Okay? So this certificate of appreciation is awarded to scientist Marcela Navacero for serving as the resource person on the topic Biology of Fall Armyworm during the webinar entitled Management of Fall Armyworm, held on 6 December 2021 via Zoom, given the 6th day of December 2021 at the National Crop Protection Center, College of Agriculture and Food Science, University of the Philippines, Los Baños, Laguna, Philippines, signed by our director, Melvin D. Buenga. Scientist Marcela Navacero. Next is Mr. Gideon Aris Borgoño for serving as the resource person on the topic modeling and remote sensing fowl infestation in corn. Okay. Next is we thank you, Ma'am Dr. Barbara L. Kawili for serving as the resource person for the topic entomopathogenic nematodes as biological control agents against fall armyworm. Thank you po, Ma'am Bambi.
Maraming salamat.
Next is, we thank you, Ms. Melissa P. Montecalvo, for serving as the resource person in the topic, potential entomopathogenic fungi against fall armyworm. Salamat po, Ma'am Aiza.
Thank you, Ms. Joy.
We also thank you, Ms. Marie Joy Beltran, for serving as the resource person in the topic, natural enemies of fall armyworm. Salamat, Ma'am Marie.
Thank you, Ate.
Okay. And we also thank Ms. Karen Ardes for serving as the resource person sa topic na insecticide resistance management. Ma'am Karen, thank you very much.
Thank you, Joy.
And last but not the least, we thank you, Mr. Randolph Cantano, for serving as the resource person at the topic, Grow Asia's ASEAN FAO Action Plan. So Randy, salamat po ng marami.
Thank you, Joy. Thank you, everyone.
Okay po, marami pong salamat sa bawat isa, sa lahat po ng ating resource speakers, sa ating mga attendees. At para po tayo makatanggap ng ating naka-flash na po ang ating link. Para po makatanggap tayo ng ating e-certificate sa webinar po na ito, maaari lamang po nasagutan ang evaluation form. Naka-flash po ngayon sa ating screen. Ang link po na ito ay makikita din sa chat box sa Zoom at sa comment sections ng NCPC YouTube at NCPC Facebook page. Maaari pong sagutan ang link po na ito para makatanggap po tayo ng e-certificate. Okay. Para po sa panghuling bahagi ng ating programa, tayo po ay bibigyan ng mensahe ng ating NCPC Deputy Director na si Ms. April Alvear. Ma'am April.
Isang maganda at mapagpalang umaga po sa ating lahat. Isang 60 katumaapaw na webinar po ang ating napakinggan at napanood sa umagang ito sa tulong po ng ating magagaling na researchers na nagbahagi ng kanilang iba't ibang kaalaman at resulta ng pananaliksik tungkol sa mapaminsalang fall armyworm. Marami pong salamat kina Scientist Marcela Navasero, Mr. Gideon Aris Burgonyo, Miss Melissa Montecalvo, Miss Marijoy Beltran, Miss Karen P. Ardes, Mr. Randall Candano at sa aming Associate Dean for Research and Extension, Dr. Barbara Kawili. Sa atin po mga nakasama sa umagang ito, sana po ang inyong mga natutunan at nalaman sa ating webinar ay inyong magamit upang mapamahalaan o masukpo ang matinding problema sa PAW. At inyo din pong maibahagi sa iba't pa nating kasamang magsasaka na hindi po natin kapiling ngayong umaga. Marami pong salamat sa patuloy na pagsama at pakikibahagi sa aming mga webinar. Sa buong webinar team, sa pangunguna ni Ms. Charlotte Hagosohos, as extension team sa pangunguna ni Ms. Romalyn Limpiada Miras, maraming salamat sa pag-iisip at paghahatid ng mga makabuluhang webinar na makakatulong talaga sa ating mga magsasaka at iba pa nating kasama sa agriculture sector. Ito na po ang huling webinar ng NCPC sa taong ito. Ngunit hindi dito nagtatapos ang pagtulong at paglilingkod ng aming tanggapan. Maaari pa rin po namin kayong matulungan at masagot ang inyong mga katanungan. Kayo lamang po ay magpadala ng inyong mga katanungan sa aming email at Facebook account at ito po ay aming tutugunan. Muli, ang NCPC po ay laging handang tumulong at maglingkod sa tao at sa bayan. Ako na po ang unang babati ng isang masaya at ligtas na Pasko. Muli, maraming salamat po at magandang umaga po sa inyong lahat.
Maraming salamat po, Ma'am April. So, ito na po ang huling NCPC webinar para sa taong 2021. At para po sa mga latest na updates mula sa aming center, maaari po kayong bumisita sa aming website, ncpc.caps.uplb.edu.ph. Pwede niyong i-like, i-follow at mag-subscribe sa aming pong FB page, UPLB CAPS National Crop Protection Center at National Crop Protection Center UP Los Baños YouTube channel. Muli, ako po si Mary Jo Mendoza on behalf of the NCPC Webinar Series team. Kami po ay nagpapasalamat sa inyong pagdalo ngayong araw. Mabuhay po kayo and stay safe.
Maraming salamat. Congratulations, NCPC.
Thank you.